All right, let's take a look at Bluetooth Classic. We're going to take a look at Bluetooth Classic, describe the technology, talk about how devices join the networks and so forth. Take a look at some of the risks in using them, how we can discover and potentially interact with Bluetooth, examine the authentication exchange, and then ultimately look at some of the other things that could potentially go wrong in the protection mechanisms that they've used to prevent sniffing, monitoring, discovery. In my opinion, Bluetooth Classic, between the stuff that we're seeing for Bluetooth and some of those other technologies where similar types of technologies excel, I'd argue that Bluetooth is the most secure, specifically in the way that they've chosen to use the radios in such a complex fashion, and it makes it, the barrier to entry to capturing data is significantly greater with Bluetooth Classic, and we'll talk about that as we go through. So Bluetooth was intended to be a cable replacement technology, so that we didn't have this whole mess of wires, heavy, moderate amount of bandwidth for us to do keyboards, mice, some audio, and those types of things. So not super high speed, not super high bandwidth, but somewhere sort of in the middle to be able to get rid of some of these cables. When I first started seeing the advent of Bluetooth technology, I never thought I'd have a Bluetooth mouse in my at home because the other mouse was tied down by a cord. Because we have cats, and what happens to cats? They do the YOLO. They go up to stuff on the desk and push it off the desk. And if it's a Bluetooth mouse, there's no cord keeping it tied to the desk, so they just swipe it on the floor. It ends up under the refrigerator. Yeah, this is also how we know that the world is not flat, because cats would have pushed everything off the edge by now. Okay, see my dad jokes again. Okay. All right, so we do have Bluetooth mice in the house now, and our cats do pretty good, and sometimes they do knock them off my desk, but it's not as bad as I expected. Okay. Bluetooth is defined by the Bluetooth Special Interest Group. They're a group that fully encompasses the development of the technology and the marketing. So it's sort of a combination of the Wi-Fi Alliance from the certification group and all of the engineering groups like the IETF and the IEEE. They build the specification in its entirety. And the Bluetooth Special Interest Group over the years has seen that we are, as humans, are fundamentally using technology differently as time has gone on. And they've attempted to make Bluetooth technologies competitive in those realms by also evolving, in some cases, to be able to provide us more bandwidth, lower battery consumption, ease of use, and simplification of the protocol, so that it can be used across a wide variety of devices. And that evolution has gone from Bluetooth Classic to Bluetooth Amp, and now into Bluetooth Low Energy. And I still sort of classify Bluetooth 5 as Bluetooth Low Energy, in that the technologies are very similar. Bluetooth Classic, the single most popular Bluetooth technology in use. Keyboards, headsets, automobiles, mice, audio, speakers, you name it. Lots of it available. Reasonably placed for bandwidth, 2.1 meg per second effective data rate, using 2.4 gigahertz frequency hopping spread spectrum. And as a result of these design choices for how it is using the 2.4 gigahertz spectrum, gives it a high degree of interference immunity. And then as the technology evolved and our adoption of the 2.4 gigahertz spectrum became more ubiquitous, they also changed the way that frequency hopping changed. To be adaptive frequency hopping. So if it was hopping into an area that had lots of RF noise or some other technology, it would change its channel hopping pattern to avoid those areas for periods of time. So stay out of the place where the noise is. It's like me going to the restaurant and sitting down next to the live band. I just don't go to that restaurant on Tuesdays because I know there's always a live band on Tuesday. So do some of those types of things. Okay, so when we say Bluetooth, we typically mean Bluetooth Classic, unless we specify otherwise, such as low energy or amp. So looking at this a little bit more visually, Bluetooth uses frequency hopping spread spectrum. And it has 79 channels available in the 2.4 gigahertz spectrum for Bluetooth. And it hops between those channels 1,600 times a second. So it hops really fast. I don't think Hedy Lamarr ever realized that they would be doing channel hopping this fast. The documentary that I saw was really great, and was disappointing that she really never got the credit she deserved. So it hops between all of these 79 channels throughout the entirety of the 2.4 gigahertz spectrum at all times. And on the slide here, we have some images. And on the left is, left and right, there are two Wi-Fi access points in use. And on the left, we have a Wi-Fi device on channel 1, 2412 roughly, for the center frequency, using direct sequence spread spectrum. Meaning we have a center channel, we have 10 megahertz of bandwidth on either side, spread across the spectrum for one channel, and we have a direct sequence. We do some hopping as needed within that 20 megahertz wide channel. On the right-hand side, we see similar types of things at the top, but the one on the left and the top is a low utilization wireless network. Maybe one client connected to it, not sending traffic, and just some ARP requests and replies. The one on the right with the filled in bar is a direct sequence spread spectrum wireless network that is under heavy utilization. The hops in that spectrum are faster because we need to deliver more data, so it's doing it faster and occupying more of that RF space. However, this swath right across the middle with all these little dots, that's Bluetooth. So it's not using one channel and a chunk of bandwidth. It is using all of the channels and little chunks of bandwidth and hopping between all of those areas as time progresses. Now, thinking about the adaptive frequency hopping and the interference immunity, when one of these devices hops into here, there's other RF energy present there, and maybe we lose that signal. But it's only there for 1/1600th of a second. Well, maybe it bounces around in here a couple of times, but still for very, very short periods of time. And if we now note that we lose packets when we're on these channels, we'll avoid these channels for a period of time with the adaptive frequency hopping. Okay. One other point I wanted to make. The channel hopping patterns for Bluetooth Classic devices are unique. They are based on the device's BD adder, and the BD adder is a MAC 802 compliant 48-bit address. So every Bluetooth device has a unique address. It's a MAC address, effectively. And just like many of our other network devices, they have unique MAC addresses. So each device has its own unique channel hopping pattern. When we have two devices that need to talk to each other, they need to synchronize those channel hopping patterns so that they can be on the same channels at the same time for send and receive. So there's a process that we'll need to go through to synchronize those radios. Looking at the power, output power of the transmitters, most Bluetooth Classic devices operate at class 2. Meaning that their output power is set at 2.5 milliwatts, giving us an effective range of about 10 meters. We can do lower power to conserve battery with class 3 at 1 milliwatt for about 1 meter. And we can do high power for longer distances, affecting battery life, of course. The more power we need, the more battery we need. For class 1 at 100 milliwatts, or an effective range of 100 meters. Now, your Bluetooth adapter, the Perani Sandy UD100 that you have as part of the kit, is a class 1 device. It is the highest power, so great for communicating at long ranges, but will draw more power from your USB port as well. Okay. Typically, we find that phones are at class 2, but that impacts your battery life more than a device at class 3. So why don't we use class 3 on our mobile phones? Save battery life. It becomes a usability problem. If we think about class 3 at about 1 meter, we take our phone and a Bluetooth headset, and we put the headset here, and we put the phone in our pocket, and we've now introduced a nice, good barrier to 2.4 gigahertz energy, water, our body, in between the two. So we're effectively reducing that range. So it is pretty likely that those headsets will disconnect if we put our phone in our pocket and the headset in our opposite ear, just because of the barriers to RF energy. Also, if you're like me and you're in my office on a conference call, put the phone down on my desk and I put my headset on and I pace. And there goes my call. So from a usability perspective, having the phone at class 2 makes sense. If you think about this action, I'm 5'7", so that's not too bad. But imagine how much meat and distance you're putting for somebody like Shaquille O'Neal. Like, that's a lot of distance, and that's a class 1 wouldn't work for Shaquille. Class 2 makes a heck of a lot more sense to be able to conserve battery power. So you guys do have a class 1 device, and with a removable antenna, and we'll talk about that a little bit too. All right, a brief introduction to Bluetooth AMP. Bluetooth AMP stands for alternate MAC and physical. So alternate MAC and PHY, so physical layer and MAC layer. The intent here with Bluetooth AMP gives us the ability to have increased bandwidth for higher speed, lower latency latency data transfers. What the Bluetooth Special Interest Group saw was that the 2.1 meg effective data rate, as we started to evolve to consume more high definition media and music, that wasn't going to cut it for that bandwidth wasn't going to cut it to have good quality audio. So they realized they needed to have a method to do so at a lower latency, higher bandwidth option. And they found that the easiest way for them to do so was not to redesign Bluetooth at all, but in many of the devices that we were doing this type of data exchange with at higher bandwidth, was in a device that already contained another radio that could do that really well, like Wi-Fi. So what really ended up happening with Bluetooth AMP is that you use a Bluetooth Classic connection to exchange SSID and key information to stand up a wireless access point with one of the two devices, and then having the other one act effectively as a client, so that we can create a wireless network with shared credentials over Bluetooth, trigger the setup of a Wi-Fi network over Bluetooth, do our high-speed data transfer, and then shut the wireless network down. We're done. That's the alternate MAC and physical layer. So they're using Wi-Fi, they're using Bluetooth to create Wi-Fi with a separate Wi-Fi radio. That's pretty cool. Now, I haven't seen a lot of people use Bluetooth AMP, and I think it comes under a bunch of different names, depending on your technologies. I was doing some reading. I was looking at Wi-Fi Direct the other day as some prompting, and I'd seen some ways about doing Wi-Fi Direct by setting it up via Bluetooth and then switching to Wi-Fi. So, but specifically looking at the AMP side, we don't see a lot of folks using Bluetooth AMP. And maybe we'll start seeing more of it, depending on how things progress for how we use data. Good point. So a lot of the vendors started to do their own thing because they didn't want to do it this way, or they were ahead of the standard already. So that makes absolute sense. And so again, and maybe another reason why we don't see a lot of AMP. However, I think that, by looking at the data that we have availability to, we don't think that a lot of people use AMP, in that with Bluetooth AMP, it creates an access point with some very specific strings and names that we can search for, such as AMP and a MAC address. So if you go to search for Wiggle for these types of access points, there are limited numbers of reports for these types of access points. So that would indicate not a lot of people use them. Miracast is likely the technology that is similar to Bluetooth AMP, and that they were potentially ahead of Bluetooth AMP's development, so they went their own route instead. Similar type of techniques from my understanding, because I went and looked at Miracast as well. And when the discussion I was reading on Wi-Fi Direct, the Wi-Fi Direct and Miracast were very intertwined together. Oh, they do it here like Miracast, and Miracast does it like this. So similar types of things. A proprietary method as opposed to Bluetooth AMP being now potentially a third technology to those. So that said, Wiggle says they don't have a lot of reports for these wireless networks that are indicative of Bluetooth AMP. So that means not a lot of people use them. But I think our measurement is flawed here in that Bluetooth AMP is a very transient type of network. Hey, I need to do some large data transfer. Here's your data. Okay, we're done. Access point goes away. On, off, on, off, on, off, 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 or off for long periods of time. And the data collection that Wiggle collects is also transient. I go for a walk down this hallway. I do some recording. If there's no AMP on, I don't record it. I turn my Wi-Fi collection off, AMP turns on. So I may have missed the transient nature of AMP just in that I'm not doing continuous monitoring, I'm doing point-in-time monitoring for Wiggle. So again, opportunities for us to have missed AMP being used. That said, I still don't think a lot of people use it, but I think maybe our measurement is a little bit flawed here. Bluetooth Low Energy is a reimagining of the Bluetooth Classic stack to make it a little bit more simple, easier to implement, and give us some structured type of data transfers. And we'll talk about that at length this morning, with the intent of, with the oversimplification, also giving us the ability to power small devices with little bits of bursty data on very modest batteries, such as watches and keyboards and other stuff as well. So maximum data rate of 1 meg per second, so half of Bluetooth Classic, and also great for some power conservation and cost implementation of the stack as well. And arguably easier to use for both developers and consumers. And we'll see how that can be a potential problem. Yes, sir. Yep, Bluetooth Classic is Bluetooth 1 and 2. Bluetooth AMP is Bluetooth 3. And Bluetooth Low Energy is Bluetooth 4. Bluetooth Low Energy, in my opinion, also includes Bluetooth 5 because they are very similar, although they are now just referring to that as Bluetooth 5 in addition to Bluetooth Low Energy. 4 is completely different than Bluetooth Classic. Bluetooth Classic at 1 and 2 has its own physical layer and MAC layer. Bluetooth AMP is using Bluetooth Classic to do Wi-Fi, so alternate MAC and physical layer. Bluetooth Low Energy retains some of the Bluetooth Classic mechanisms and physical layer, but different structured for the data and channel hopping patterns and some of the security. So all very incestuous, all sort of blended together, but definitely an evolution of the technology and some changes to make that happen. All right, so let's take a look at the Bluetooth protocol stack. We have the radio interface and RF controller, the baseband controller and packet construction, framing, the link management protocol or LMP for building our network, and then our host controller interface, our HCI layer, and then a bunch of our logical link control, profiles for the type of data that we're going to be exchanging, and then our application layer, whether it be PPP, IP, or some other type of structured or unstructured data. The problem that we have here with Bluetooth, specifically when we start going into audit and sort of pen test mode and interaction mode, is that a standard Bluetooth dongle, and as specified by the Bluetooth Special Interest Group, the only place at which a user can interact with the Bluetooth dongle is through the HCI layer. If you want to create a packet on Bluetooth, you send your formatted data to the HCI layer, and it will say, okay, you want to send it to that device? Great, we'll put those addresses in a packet for you. We'll construct the packet and we'll send it out in the air for you. You just give us the data, and everything below the HCI layer is handled for you. Oh, you want to create a packet, you want to create your frame, and you want us to tell what channel you put it on? Nope, sorry, you can't do that. So all of the really good parts for packet sniffing, packet creation, channel changing is abstracted in hardware by the HCI layer. So we don't have direct access to all of the good parts like we did with Wi-Fi. But we'll find some solutions to these problems as we move through the module. Now, my favorite part about this entire slide is that we have to note that the Bluetooth dongle and the laptop are not to scale. And you know that when there's a warning message, it is because someone has complained about it, right? That's why they have the hot coffee, the caution hot on the coffee at McDonald's, because McDonald's got sued because the coffee was hot and they allegedly didn't know. Yeah. It says it's not to scale because someone at one point said, hey, those aren't to scale and I'm offended, type of thing. So yeah, it wasn't quite that bad, but still there's a good joke in there regardless. So I demanded that we leave the not to scale thing there because it's true, they're not to scale. That would be really awkward if it was. I don't think Bluetooth would have taken off. We take a look at Bluetooth addressing. We mentioned a little earlier that Bluetooth channel hopping is based on each device's unique BD adder or a 802 compliant 48-bit address assigned uniquely to the device. And we start using this unique per device address as a secret within Bluetooth for a couple of different components of its security mechanism. So looking at the address, we have three different portions, 24 bits of lower address portion with the least significant bit on the left there, the upper address portion in the middle-ish for the UAP, and then we have the additional 16 bits of the insignificant address portion, or the insignificant address portion. I guess IAP doesn't sound as nice, but NAP does. All right, looking at some of the other portions of the protocol, looking at the baseband header before we start constructing packets, we'll tag these parts onto the beginning and the end of our packets. With the Bluetooth baseband header, we're not using the MAC address for source and or destination addressing. When we join devices to the Bluetooth network, the PicoNet, we get an address assigned to it from the master called the logical transport address. And that logical transport address is one of 7 values. So we can have up to 7 devices in a Bluetooth network. And we can extend that by taking one device in the network and creating another master so that we can form a scatter net. So when we join the network, we're provided an address which is significantly shorter than a 48-bit address. And it's 3 bits as opposed to 48. And then we also specify the types of packets that they are in the baseband header so that we know the speed in which we should prioritize processing it, kind of like quality of service, and how much data is to be expected, i.e. the number of slots that this packet will occupy. Now we start seeing here the baseband header has a checksum, the header error checksum, or the HEC of 8 bits at the end. And that checksum is calculated with a standard algorithm, but it uses a secret input. It's HMAC variety of a hashing algorithm, similar to what we saw with WPA2 pre-shared key. Now with that, the input, that secret into that header error checksum, for that HMAC variety of the algorithm is the upper address portion of the Bluetooth address. So this is one of the times where we're using that BD adder as a secret, as a key for calculating that checksum. So we can't recalculate that checksum unless we know the BD adder. And this becomes a specific challenge in that the only addresses that we see in these packets are the logical transport address, not the BD adder. And the BD adder is typically not broadcast in the air, so we don't see it. We'll talk about some ways in which it is broadcast in the air and or have some ways in, that we can recover that. All right, we want to start joining the network. Link management protocol will negotiate with the devices in the network to determine feature sets and capabilities and verify whether or not we should actually participate in these connections. We have our two devices, and the link management protocol will negotiate which version we're going to speak and what types of devices they are. So the first one, the master will query the new device on the network to say, hey, what type of features do you have? Oh, I'm a keyboard. Great. So they respond with the features. I'm a keyboard. The master of the network, I really like keyboards. We allow keyboards to connect to us. We don't like headsets, so if you were a headset, I told you to go away. Okay. Host connection, yep, absolutely. We can use a keyboard. We allow keyboards to connect to us with the connection request. Okay. Then the new device asks, what version of Bluetooth are we going to speak? 1.1, 1.2, 2.0? And the master responds with an appropriate version. If that works out, the new device says, yep, great, I'm a keyboard, you like me, and we have a version that we can agree on that we're going to speak. Can we finalize the connection? The master of the network says, yeah, absolutely, let's continue speaking with each other. The data exchange happens, and then maybe we remove our phone from the car, so we issue a detach. We get removed from the environment. The fun part here is that any time during this exchange, a link management protocol can potentially have a disagreement with the two devices. Hey, what are your features, new device? Oh, I'm a headset. Oh, we don't allow headsets. We don't allow audio output on this device, so go away. LMP not accepted of a bunch of variety of message types. Any of these LMP not accepted and used in the right place, we can effectively create denial of service conditions. This is a deauthenticate, disassociate type of request. So there's a legitimate need for the protocol to say, yeah, go away. We don't like that you're a headset. We have some specific restrictions preventing headsets from joining this device, but we like keyboards. So no headsets today. Thank you. Maybe it is a keyboard, and the keyboard only speaks Bluetooth 1.1. And the master device says, no, we only speak Bluetooth 2.0. We're never going to come to an agreement about the language we want to speak. So sorry, I guess we're not going to communicate today. So LMP not accepted, version mismatch, those types of things. And we'll talk about some denial of service techniques using LMP not accepted messages for being able to perform, reperform some of these operations. So for us to start joining the network, we need to do a couple of things. As we mentioned, each device has its own unique BD adder or MAC address, which determines its own unique channel hopping pattern. So each device has its own unique channel hopping pattern based on its BD adder. When we try to talk with two devices, they're channel hopping in different places. So we need to put those channel hopping patterns in sync. And we do so by going into discoverable mode so that we are in fact transmitting our BD adder into the air so that the devices can observe them. We can then switch to one channel hopping pattern one channel hopping pattern for the PicoNet, the Bluetooth network, and then we can synchronize those radios. The problem is that if I find the master in discoverable mode and I want to join that network, and I change my channel hopping pattern to be that of the master's BD adder, I can now calculate what that unique channel hopping pattern is. I don't know where in the pattern the master is. The master could be 30 steps in to the channel hopping pattern, and I just calculated it, and I have to start at position 1. So we know what the patterns are, but we're not in sync. We're potentially off by 1 or off by 30. So in order to fix that, we go into page scan mode, which is doing the tortoise and hare approach, meaning that the master device will speed up its channel hopping to 3,200 times a second, while the new device is still going at 1,600 times a second around in that pattern. And the master will start sending packets basically saying, hey, I'm here, and the new device will receive those packets, the directed access queries, and eventually they will have a match in that. I see this as like auto racing or like NASCAR when they're driving around in a circle, and the lead car is going so fast compared to the last car that it eventually comes around and laps the back car. So tortoise and hare approach, in that we have one speed up significantly faster in an attempt to lap the slower one, the one at 1,600 times a second, multiple times. And this approach doesn't always work on the first go around, so we potentially have to do that multiple times to have those two radios in sync. Once we have that point where we know that we were in sync, a master slows back down to 1,600 times a second. This is why it can take a couple of seconds for these devices to join a network, is because we're engaged in a fairly complex operation for changing our channel hopping to 3,200 times a second. Once we've joined the network and we have the HCI layer dealing with all of our packets for us and whether or not we're connected, we need to consider the types of data that we're going to now send in our packets over this new connection. And Bluetooth has a bunch of different types of profiles in which they will choose how they want to format the data in its various varieties for any given profile. And any given profile can choose to format their data differently. There's all sorts of ones for depending on the type of methodology you want to use and the functionality. And each one also has their own independent security controls. So we can do encryption, we can do authentication, or we can choose to do none for each one of these profiles. And it is independently controlled by the implementer. So a Bluetooth headset from one manufacturer can have encryption and authentication, but another Bluetooth headset for the ultimate headset. Why it's ultimate, I have no idea. Everybody's head perked up when I did that, my radio announcer voice. And why ultimate headset, no idea. One manufacturer can implement security, another manufacturer can choose to implement no security. So it's based on the developer's decisions there. So all independently controlled. Right. We can do all sorts of fun stuff. Bluetooth network encapsulation protocol sounds like a good idea too, to do IP over Bluetooth. One of the other ones that I've seen from some attacks some time ago was the RFCOM serial port emulation. There was a set of Nokia phones popular in the early 2000s. Those are the Nokia phones that you could actually use as hammers, right? The indestructible ones. That one of the Bluetooth profiles didn't require any authentication or encryption, and it was the RFCOM serial port emulation, and that RFCOM serial port was tied directly to the cellular modem, so you could pair with a Bluetooth device, no security, no PIN, no encryption, and you could interact with the serial port connected to the cellular modem and issue AT style commands, as in AT-DT, so you could make the cell phone dial phone numbers with no interaction from the user. Yeah. That was pretty neat. We saw attacks about that in London with some folks walking around the tube stations with a rolling bag that was just connecting to phones that were vulnerable to this, making them dial those per minute charge numbers, like here in the US, 1-900 numbers. Now, no one they would answer, and there would be no one on the other end, and the phone would be in someone's pocket or bag, and they would have no idea that it had dialed. And then they go down into the tunnels to get on the tube, and it would disconnect. But the attackers were sending these calls to their 1-900 numbers and billing them potentially many pounds per minute. At the end of the month, you get this bill, and your bill is 400 pounds. Like, whoa, what just happened? And then you have questions to answer to your significant other. Why were you calling 1-900 numbers? Right? Yeah. I didn't. It wasn't me. Clear, it wasn't. They were right. So there's all sorts of potential issues with some of these profiles. These profiles have very uniquely named modes. They're very descriptive in their naming. The security profiles can choose to implement a different level of security depending on each implementation. Mode 1, no security at all, no authentication, no encryption. Mode 2, no link encryption, but we are potentially doing some additional application security layer options within the protocol itself for how we've chosen to structure our data. And mode 3, we do link encryption, which does require us to perform some authentication, i.e. an exchange of pins. Okay. So effectively, mode 1 is an open Bluetooth network. Mode 1 profiles are open and can be connected to by anyone without a PIN. You just need to join the network once the device is in discoverable mode, and then you can continue to interact with those devices. Mode 2 and Mode 3, if I remember correctly, I know Mode 3 requires the use of a PIN so that we can derive encryption keys. So there is some authentication there. So looking at that link authentication, specifically looking at Mode 3, we do need to have some authentication. We do so with a pairing operation where a user needs to enter some unique data as use for input into some encryption key generation. And that would be the user selected PIN. We take that PIN and we mix it with the BD adder, which is a secret, to generate 128-bit key content, using the modified Safer Plus cipher to generate a hash, which we're then going to use the transitive property of XOR to create encrypted data. Okay. So if we authenticate, we type the PIN in the same on both devices. That PIN is used with the BD adder to generate some keys, which we then use to encrypt data, take plain text transitive property of XOR to send ciphertext within the packets. So that encryption that we are using with that key is a cipher that the Bluetooth Special Interest Group developed themselves. Is it a good idea to develop your own cryptographic cipher? Never, never. So they developed a cipher. They didn't learn from history, right? And their cipher is called E0, and it was intended to be powerful yet simple to use on a low power set of chipset. It is similar to RC4 in that it is a stream cipher. You need 100 bytes of data to be encrypted. Great, tell us how long your data is and we'll give you PRGA output from E0 using our PIN and our BD adder with modified Safer Plus to generate a hash. And we'll give you 100 bytes of PRGA, which you XOR to get 100 bytes of ciphertext. Cool. Now, E0 has been found to have been broken. It's fairly hard to do. The thing that we do have here, aside from the BD adder as a secret, is the PIN, which is sometimes user selected. The Bluetooth Special Interest Group says that the Bluetooth PIN should be between 1 and 16 characters, 1 and 16 numbers. Has anybody ever used a 1, 2, or 3-digit PIN on their Bluetooth stuff? Me either. The lowest I've ever seen is 4. I'm typically now seeing 6 to 8. Okay. And in many cases now, I'm not even given the opportunity to pick my own pin. The pin is derived for me by some mechanism. Like if I try to go attach a keyboard to my Mac, it pops up and generates a pin for me, and I have to type that in on the keyboard. My new to me truck, I moved into the 2000s, as it were. I moved into a modern vehicle. It's still a 2013, and it has Bluetooth, and it selected the pin for me, so that I had to type that in on the phone. So in many cases, it will select one for us. However, what do we do when we have a device that has no man-to-machine interface? We have no keypad to type in a number, like a headset. Well, those headsets come with these nice little manuals in which it has Morse code to number table in it, so that when you want to pair your headset, you tap it lightly with the Morse code on the table. No, it doesn't. That would be really frustrating for users to do. They'd have to look this stuff up on the table, and they'd have to get the taps right. And many of them don't understand the difference between a dot and a dash. And yeah, no, they do fixed pins on the devices with no man-to-machine interface. Typically 0000, 1111, or 1234. Hey, that's the combination of my luggage. So many of these fixed pins across multiple devices, in which this is used as a secret, and now we have a shared secret across multiple devices, multiple manufacturers, and many of the default pins are standard and well known. Bluetooth is intended to be relatively short range, 100 meters at class 1, which is pretty long. However, we can extend that range by changing our antennas. So a class 1 device at 100 meters, class 2 at 10. However, we can extend those ranges, and this is the way we used to have to do this, because none of the class 1 devices were manufactured with removable antenna connectors. The Perennisana UD100 that you guys have as in class is the only Bluetooth adapter that I'm aware of on the market that has a removable antenna at class 1. Every other class 1 device has a fixed antenna. And like this Linksys USB BT100 used to have a little flip-up antenna. And what you do is you take a screwdriver and you pry the glue apart for the case. You remove the case, you desolder the antenna, and then you solder on your own RPSMA pigtail. And then you go put it back together, and it doesn't like to fit back together because you've pried the glue apart, and you've got these screwdriver bite marks on the edge, so they're kind of sharp. So you use some zip ties, maybe some super glue to put it back together. You want to do that in case you have to fix it. Some zip ties to put it back together, and then you cut the ends off, and always these parts where you cut the zip ties off are sharp. So this is a really professional looking device to bring to your customer, and will probably injure you 3 or 4 times with the sharpness, right? This is why I really like the Perennisana UD100, because it's done for us. This is the way we used to have to do this. Okay? And we can add new antennas on these class 1 devices to be more directional and higher output power with the effective radiated power based on those designs. To the point that there was some work done in the mid-2000s where a gentleman created the Bluetooth sniper rifle. You guys seen this? Yeah, he took a 2.4 gigahertz Yagi antenna and put it on a rifle stock, just empty rifle stock, no explodey bits, no barrel, and put the Yagi antenna where the barrel would go, and connected it to a class 1 Bluetooth device. And with direct line of sight, they went out into a balcony of a hotel, direct line of sight down to the piers, and did a Bluetooth pairing to a class 2 cell phone from over a mile away. So thinking about the pairing, we connect the devices. We need to do some authentication for one of our services with mode 3. The user inputs a PIN. We take some keys and we store those on the device for later. Very similar types of techniques, just using different algorithms, stream ciphers, XOR, user-derived input. And then every time we reconnect to the network, we reuse that same key for the device. And we store it on both ends. This reminds me very similar of WPA2 pre-shared key, similar types of mechanisms. Swap out RC4 for E0. Swap out HMAC MD5 for Safer Plus. Similar types of things. Now, when we do some of the pairing, we need some additional math, i.e. the four-way handshake that we saw with WPA, WPA2 of either pre-shared key or enterprise. We do similar type of mechanisms with Bluetooth Classic to do authentication between the two devices with our output hashes for encrypted data by using some nonces and some math and some message integrity checks. So going through this process, we calculate our initial keys on our master, the K init, using our pin with the BD adder of the slave that we found in discoverable mode, and an in random number, a random number. We calculate our initial keys, we send the random number to the new device. The new device receives that random number. Cool, now I have a random number. I can begin calculating my initial key using the pin that we entered, my BD adder, and that new number. So now I'm going to send another random value back to the master. The master is going to take that with kinit, the new nonce that it's received, the combined key, do some math and send a new nonce back to the slave, to the new device. Take both of those keys using kinit, both BD adders, and now do challenge response. Let's derive some keys with some nonces, then we'll do challenge response. We'll use those keys to calculate challenge response mechanisms to verify that we had the right keys and the right pins and the right BD adders. This is a four-way handshake, but it's 1, 2, 3, 4, 5, 6, 7, 8, eight-way handshake. It is overly complicated for generating more keys to beget keys, and this is like terribly confusing for us to start walking through this process. The point here is, this is done over the air. We are sending our random numbers, our combined keys, and we have observable signed responses, the message integrity checks. This is like step 3 and 4 for the Bluetooth, for WPA, WPA2, four-way handshake. And these are of the variety of the nonce exchanges in steps 1 and 2. We're just doing it multiple times. They are in the air. They are in clear text. If we can sniff Bluetooth, we can observe them. This is a massively complex operation for something that we can sniff. We can observe the BD adders in discoverable mode, which the devices need to be in discoverable mode so they can join the network. So we can observe the BD adders potentially too. There's one piece of this whole exchange, this whole complicated exchange, that is not in the air, that is a secret. What is it? The pin. Just like WPA, WPA2 pre-shared key, and WEP, there's one piece that was never sent in the air. We can observe everything else. The pre-shared key. What is the pin comprised of in Bluetooth? Typically 4 to 16 characters, usually 4 to 8 characters, and those characters being digits, numbers. There's not a lot of entropy there. So if we can observe all of this, we can potentially recover the pins, meaning we can have all of the encryption keys for these devices so we can decrypt data. The challenge really becomes, as we've seen because of the HCI layer, is getting this data because we don't yet have the ability to sniff these exchanges. If we can catch them, we can calculate, we can do an offline pin attack, pin brute force attack by calculating all of our random numbers, go through that process by pulling those portions out of a packet capture or in a CSV file or typing them in manually, and then calculate based on a pin input that we cycle through all of the numbers, 1 through 16 characters. And it's not a complex math operation. It was intended to be in small hardware, so Safer Plus and E0 are very fast. And then we can mount an offline pin guessing attack. We can do so with BTCrack. We can load all of the values from those observations in from a CSV, because those are lots of values for us to type and potentially mistype. And in this case, loaded the values, hitting crack, and 93, almost 9,400 pins per second. And it did recover the pin 230739 in 3.6 seconds. That's fast. Again, the challenge becomes getting the data to begin with, because we don't yet have the ability to sniff some of that stuff. Some things for us to think about going into CTF day. You may, as part of one of the challenges, and I'm giving you a really, really big hint, you may be cracking Bluetooth Classic pins. So you can immediately see yourself going and downloading a copy of BTCrack for Windows. Don't. Because you go and search Google for BTCrack, and you can find the binaries on some really shady site that has lots of pop-ups with adult content and all that type of stuff. And it's just not one of those websites you ever want to visit, because your antivirus starts going off like crazy. Okay. Then you download it, and antivirus scans it, and Windows Defender says, "No, danger, Will Robinson," but you install it anyways because you want to win CTF. And then you run it, and then it says, "Sorry, we're missing some DLLs." So then you go search for these DLLs, and you download these DLLs from equally shady websites that your antivirus goes off like crazy. And yeah, let's go put random DLLs on our Windows system, right? We've already done random executable. Let's add random DLLs to the mix. And yeah, terrifying. Don't do it. There is a Linux command line version written by one of my former students in GitHub. It's as simple as doing git clone from his GitHub repository and doing a make, and it makes you a version of BTCrack that has similar functionality from the Linux command line. Typical real world scenario. Oh, I got to go do this attack because they're vulnerable to this thing. Oh, I don't have any tools to do so, but I know what the tool is that I need to use. So looking at this practically, we have to be able to capture some of that data. We'll overlook the fact that we have some challenges for sniffing Bluetooth. However, if we can sniff Bluetooth, we have some logical places in which we can go capture this traffic. Like go sit at the Starbucks or the Panera Bread next to the local AT&T store. So when folks go in and get new phones and the AT&T store staff are very helpful, "Hey, can we get you all up and running right now? Can we pair your headset that you're wearing to your new phone? Or would you like to buy a headset? And before you leave, let's get it paired and make sure it all works." So, as the actual operation is happening. We also talked about some LMP not accepted messages as a DOF. In the case of the pairing operations, LMP messages can be sent at any time. So we could be sitting in the AT&T store in Starbucks and have folks in there already in Starbucks with paired devices talking on their headset. And we could potentially inject LMP not accepted, claimant has no link key message. Meaning, hey, I was paired to you before. I know we were paired before. We negotiated some keys, but I lost them. Can we renegotiate keys? Can we reinitiate a pairing request? And then we can observe that exchange and then brute force pins. Yeah, that's called very similar to WPA2 pre-shared key of the denial of service attack. Hey, go away, rejoin the network and observe the exchange. Similar types of things. So that's the deauthentication based attack for Bluetooth Classic. The challenge becomes also non-discoverable devices or devices in non-discoverable mode. If they're not discoverable, we aren't able to observe the BD adder, meaning we can't find the channel hopping pattern, meaning we don't have the BD adder to input into the key derivation function for the encryption. We also can't calculate the header error checksum because we don't have the BD adder upper address port part. So we need the BD adder. It's really important for us to be able to communicate and delve into those secrets for Bluetooth. However, the Bluetooth Special Interest Group says you may want to put your devices into non-discoverable mode so that other devices can't see your Bluetooth device. You can still use your Bluetooth services like talking on a headset, but your device will not be found by other devices. I read that as challenge accepted. Right? When you tell me something can't be done, I want to find a way to do it. So, how do we do it? Well, let's cheat. Hey, looking at some of the devices, integrated Bluetooth and Wi-Fi chipsets, and we talked about this with like the Linksys routers, that they do sequential assignment of MAC addresses. Well, while the BD adder is not considered a MAC address, it's 802 compliant 48-bit in the same length and formatting as MAC addresses. So with these chipsets that are integrated for both between Bluetooth, radio, and potentially Ethernet, internal switch, and you name it, the manufacturers often sequentially number the MAC addresses and BD adder included in that. Okay. So let's use a technology that we know how to use, that we have access to sniff, Wi-Fi, and we sniff for mobile devices in this case, MAC addresses participating in a network, and then we use Bluetooth tools to query devices off by 1, 2, or 3 in either direction of the Wi-Fi MAC addresses that we found. Looking at this iOS device, the Wi-Fi address and the Bluetooth addresses are off by 1. So AF, B0, so we went up in one direction to increment for Bluetooth. Okay. And many of the devices are different. I've seen some Android phones in which the wireless chipset and the Bluetooth chipset are from 2 different manufacturers. So their MAC addresses are not even close to being in sync. So it depends on the device and the manufacturer. But oftentimes this is the practice. So how do we conduct this attack? We can use T-Shark to grab MAC addresses by doing some filtering. So wlan.fc.subtype equal to 4. So we're looking for devices doing probe requests. Or we can just find it from data transfers as well. And in this case, we've got a couple of addresses. What was it? 58 3FA0 and FADED9 for Wi-Fi. So now we take those and we increment and decrement those using Bluetooth tools for discovery. HCI tool, for example. HCI tool, ask this Bluetooth device about its name. What's the friendly name of this device? So our wireless address was 3FA0. So let's ask for 3FA1. No response. Let's go the other direction, 3F9F, no response. All right, so maybe we didn't have the off by 1 for that device, or the Bluetooth was disabled, or it didn't have Bluetooth, but we tried. It was a valiant effort. Then we have FADED9, so let's do one down, FADED8, query Bluetooth. And we have a response, it's Josh's iPhone. So now let's do our info, get some more information on DED8. And sure enough, yeah, we do have the right Bluetooth address. It is Josh's phone, and it speaks Bluetooth 2.1. Okay, and it's a Broadcom chipset. We found a device that was not in discoverable mode by cheating. Let's do it the hard way. We use the BD adder as a bunch of secrets within the protocol itself. And the first place where we do so is within some of the baseband and so forth headers. In this case, looking at the Barker code on the wireless side, the RF side, before we start actually with the Bluetooth baseband header, we're sending some information, the Barker code and a sync word, unique per network for these packets, so that we can synchronize the reception of radios. So we have a repeating set of data that when the radio receives the data, it can level out all the things that it needs to do, and it knows that we're expecting this set of data, the unique set of data for every packet, so we know where the packet begins. It's a like pre-notification that a packet is coming. So, hey, a packet's coming. Here's your packet. So you start jumping around, you start hearing the oh, wait, I hear RF energy. Oh, I hear that phrase of a packet's coming. I know now that when the packet coming message is complete, that same phrase every time, I now know that at this point is where the data starts that I need to start decoding for that packet. Okay. And in that, Barker code has a sync word, a unique pattern. And in this case, the sync word is based on some things for our PicoNet and some other fun stuff. So before the baseband header, we have that Barker code and or sync word. We can then look at the header for each one of those, which has the lower address portion of one of the devices in the sync word. So we can observe the sync word, hey, a packet's coming, and that sync word includes the lower address portion of one of the devices, the master, for the network. So that gives us what? The lower address portion is half of the BD adder in the sync word inspected in RF before the packet even starts. Unfortunately, standard Bluetooth adapter were abstracted by the HCI layer, so we need other tools to be able to grab this. We can do this with the Ubertooth One. It's about $120 from Hackshop and others, and even Amazon. And the Ubertooth One is a Bluetooth adapter. However, it is a custom Bluetooth adapter, effectively as a purpose-built software-defined radio, which sounds weird. Software-defined radio has multiple purposes. But the intent here with Mike Osman and Dominic Spill, who created the Ubertooth One, was to create a Bluetooth adapter that you, as us as users, write the Bluetooth stack ourselves, meaning because we've written the stack ourselves, we've written the HCI layer, and we allow everything through the HCI layer, so we have the ability to craft our own packets and perform sniffing and not have any abstraction for the HCI layer. Why? Because we as a community wrote it. So we can make that HCI layer do whatever the heck we want. And we can observe the sync word with the Ubertooth lower address portion tools. The problem here that we have is that we need to capture lots of data and then count them because the Ubertooth doesn't perform any error correction when it's capturing its data. So if it misinterprets some of the RF, we may end up with some erroneous results, and it's not trying to correct them. So we capture a lot, and we may now have a device that gets captured, and it's 297002 because we missed a bit or we had a bit flipped. But there'd be, say, one or two of them. We capture a long time and then use the ones that have a larger statistical grouping of the devices. And in this case, the 9EB833 is the BD adder for inquiry scan mode, or devices looking for other ones in discoverable mode. Hey, are you in discoverable mode? And those individual packets. So those aren't going to work out too well for us. But we have 300 plus packets for these two other devices for our upper address portion, or half of the BD adder. Once we have the lower address portion, we can use this to find other portions of packets in which we can recover the upper address portion. So if we have the lower address portion, we can observe the sync word, we can observe the various piconets, and then we can observe packets coming from that device. And then each one of these packets in the baseband header, that header error checksum, to validate that the header was good, uses the upper address portion as an input to the HMAC variety hashing algorithm. So if we can capture the header, we can observe the header error checksum, we can brute force the checksum and recover the upper address portion. That's kind of cool. This is the hard way, right? It requires a little bit of inspection in RF. We can also use the Ubertooth One to make this happen as well. Okay? Capture a bunch of lower address portions from the sync words into a text file, sort them and find ones that we have lots of matching. In this case, we have a lower address portion of A656F7. There was only 18 of them, short run. And then we use Ubertooth upper address portion to specify packets for a specific device that we want to capture on. Looks for that sync word for that piconet, and then attempts to capture packets for that piconet, and then attempts to brute force the header error checksum. Now, it may take a couple of tries here because, again, we are not doing any error corrections, so we may have received bogus data the first couple of times we capture one of these packets. Okay. Now, you're asking, Larry, how the heck does it find this stuff? Because we don't have the BD adder to know the channel hopping pattern. Well, that's one thing that's kind of neat is because it is hopping 1,600 times a second during its communication, at some point, it will hop onto any one of those channels. So let's just pick a channel in the middle. Ubertooth 1 picks channel 39, sort of dead in the middle of that channel hopping pattern, and just waits for stuff to go by. Sniffs on one of the channels, and it's going by and going by. Oh, hey, there's a packet. Nope, wrong piconet. Hey, there's a packet. Oh, right piconet. Let's brute force a header error checksum. So effectively offline brute force of that header error checksum. And that header error checksum input will give us the upper address portion of the device. Now, we have the lower address and the upper address. We do not have the NAP. We do not have the insignificant portion. It's called insignificant for a reason, because for enumeration and scanning, we actually don't need the insignificant address portion, so we can use whatever values we want there. So we've recovered the lower, we've recovered the upper. Now we can use HCI tool to query the device. So A656F7 for our lower address portion. And then we brute forced 4A for our upper address portion, 4A. And we can use whatever values we want for hex values for the insignificant address portion. AAAA, FFFF, 1111, doesn't matter. It's insignificant. So HCI tool for that device. And sure enough, we found Josh's iMac that was not in discoverable mode. So what are some of the practical attacks that we can do against them, aside from having now the ability to do some sniffing with the Ubertooth 1 with a purpose-built device? What are some of the attacks, other attacks we can consider? One of the ones that I think is pretty neat is using a headset as a listening bug, not intercepting communication, not following an ongoing conversation that somebody is already engaged in with the device paired, because that has some other specific challenges, being able to follow a channel hopping pattern as fast and capture the data, and then have the pairing exchange so that we can crack the encryption. Okay, so there's lots of challenges there. This is not doing the active conversation. This is after they disconnect the call and they maybe take the headset out of their ear or leave it in the air and walk away from their phone and they go to the grocery store. Connecting to that headset as a new device and then just capturing the audio coming from that device, the ambient noise. So somebody walking around the grocery store, talking to themselves, talking to their wife, talking to their significant other, yelling at their kids to sit down in the grocery cart, you name it. I'm taking my device and I'm pairing it to your headset and I'm listening to what's going on around you. Okay. And why does this work? Because many of these headsets do not have man-to-machine interfaces and have static fixed pins. So we know what the pin is. Let's just go pair with it using the pin and then record the data. We could also inject data if we wanted to. We could inject audio. And there's been lots of pranks I've heard about doing something like that. All right, let's find some Bluetooth devices in our organization, see if people are having Bluetooth in the organization on their devices or on our enterprise devices, so that maybe they're not supposed to, and or maybe they're using devices that are not on the approved products list and so forth. If we find devices, then maybe we can do some audits ourselves. There's a bunch of different devices. There's Bluetooth scanner for Android, BLE scanner for iOS, which is low energy only. We'll talk about some other low energy tools. There's BT scanner. There's a bunch of these tools available, and we start seeing new ones all the time. This is also very much a war drive type of scenario because there are a few dedicated sensor tools There are a couple of the enterprise access point manufacturers that are now including Bluetooth in their access points so that you can perform both Bluetooth Classic and Bluetooth Low Energy scanning and discovery. So some things for us to think about for doing some security on Bluetooth Classic. Establish a policy about whether or not you want to allow Bluetooth in your environment. Consider the types and manufacturers and so forth of the devices that you're looking for. If you need some additional backing, consider referencing policies on sensitive information storage, because effectively my cell phone is it's a big hard drive with lots of information on it, and if we can access that over Bluetooth, that might not be so good. Look at policies, set some goals about what should be allowed in your environment, and if you set some types of stuff, audit them, try to interact with them, and determine their level of security for Mode 1 and Mode 3 services. Education of users about Bluetooth in hostile environments, and that hostile may be other places than you expect. Okay. Talk about PIN usage. Maybe we can use 16-digit pins, and that maybe we should unpair and repair devices with new pins with some rotation schedule. Talk to users about random devices connecting to them, because sometimes even when we do a pairing of a device, you're required to click OK. Even if we are using a fixed pin like 1111. And if they do need to do some pairing of some new devices, do so at home and not necessarily at the AT&T store, so in a, quote, secure location. Looking at the security of the devices, if you don't need Bluetooth, turn it off, right? The principle of least privilege. If you have to use Bluetooth, put it in non-discoverable mode as much as possible. We can still discover them, but it is a significant barrier to entry potentially. There's just an extra hoop that we need to go through. If at all possible, and you do need to use Bluetooth, but you only need one profile and there are 3 available, see if you can disable the unneeded profiles. And this is always not an option, especially with some of our mobile devices and printers and so forth. So, and then make sure you're up to date on your software. Looking at that Nokia RFCOM type of attack, they did have a firmware update to fix that problem, but you had to go into a Nokia store and they had to flash the update. It typically took a couple of days because they had a backlog and that type of stuff. But we can see updates with some of our Bluetooth stuff. So evaluating our own devices to reference some of that policy about what should be in the environment. Take a look at some of the existing tools, put them in discoverable mode, connect to them, see what services are available, and then potentially engage in some fuzzing. So using HCI tool info to query the devices in discoverable mode, see what services are available, attempt to interact with those services with SDP tool. If you find services that you can interact with, consider downloading the manufacturer's tools for doing population for business cards, and start examining the way they'd be used and whether or not they're using authentication. Fuzzing can also be lots of fun, and there's been some recent successes against discovering Bluetooth flaws by doing some fuzzing. Aramis found that there were a bunch of flaws in a variety of Bluetooth devices a couple of years ago, in 2017. They were doing some fuzzing against Bluetooth at the HCI layer and above. None of the baseband controller framing, you name it, using standard Bluetooth dongles to interact with the various profiles. And they found that there were various profiles and various services that all had some issues, and they found 5 different remote code execution vulnerabilities and 2 possibilities for doing man in the middle over Bluetooth. Released it, they notified all the manufacturers, did proper disclosure, and it affected iOS, Windows, Android, and I think there was one other too. All sorts of stuff can be discovered from fuzzing. I think fuzzing Bluetooth is still something that people don't consider a lot. I don't know specifically what tools Aramis used for doing their Bluetooth fuzzing, but there are some tools out there that we can use, such as Bluetooth Stack Smasher. Bluetooth Stack Smasher will interact with a Bluetooth device in discoverable mode, and then will send malformed data to all of those discovered services. It's not particularly robust. It likes to send packets way too fast so that the device can't respond to it fast enough because it's busy doing other stuff. And then it claims that maybe the device is down or maybe the device has crashed. So some modification of the source code for Bluetooth Stack Smasher could give us the ability to start slowing this stuff down. And we were starting to identify this problem, and Josh tells me that he was playing with Bluetooth Stack Smasher and he slowed down the transmission of packets so it was more reliable. But I don't know whatever happened to that code. He said he checked it into GitHub, but I have no idea where it into GitHub because I can't find it. So we talked about Bluetooth authentication. We talked about frequency hopping spread spectrum. We talked about attacks against the various profiles, some of them being open, some of them not. We talked about brute forcing pins. We talked about their power. We talked about the protocol stack, how the lower layers abstracted with the HCI, making it difficult to interact with. We talked about some tools for scanning and interrogation for Bluetooth Classic, HCI layer and above. And we also talked about some of the tools for interacting with Bluetooth, such as the Ubertooth one, below the HCI layer, because on that device, we've written the HCI layer as a community. All right, it is time for the Bluetooth Classic lab. Let's move into low energy and some of their attack techniques. All right, we're going to talk about what Bluetooth low energy looks like and where it has changed some of the Bluetooth Classic implementation. While some of the methodologies still exist for key exchange and pairing and some of these types of things, they have changed a significant amount with low energy. And we want to make sure that you're aware of what these changes are and ultimately what the impact to the security of Bluetooth low energy is for these changes. We'll talk about doing some penetration testing against Bluetooth low energy, some ideas for us to consider, and then talk about hardware, software, and some practical assessment methods. All right, so why do we care about Bluetooth low energy? From all of those sort of IoT protocols that we were discussing yesterday with Zigbee and Z-Wave and some of those types of things, Bluetooth low energy is very much a contender in those same sort of systems. I don't see that it's going to make an inroad into industrial IoT, but in many of the other aspects of our lives, whether it be printers and projectors and speakers and potentially some sort of low-speed networking and lighting control and security systems and fitness trackers and medical devices and all of those types of things. Maybe not controlling a power plant, but touching lots of other areas of our lives that can potentially have some impact and or kinetic impact into our world. I see that Bluetooth low energy, Bluetooth 4, has seen some massive adoption. One, because of the brand recognition. I could have asked my mom, "Mom, have you ever heard about Zigbee?" And she would ask, "Are those Africanized bees that are really attack you?" No, Mom. "Mom, have you heard of Z-Wave?" She says, "Is that what happens when you swim out too far and it drags you off?" No, Mom, that's rip current. Okay. "Mom, have you heard of Bluetooth?" "Oh yeah, that was that Scottish guy that always ate lots of blueberries." "Oh, no, wait, no, that's the wireless technology that I have in my phone." And she had a flip phone type of deal. Like, my mom, who was a Luddite, had a VCR Blink 12. She knew what Bluetooth was. She didn't know what Zigbee was. She didn't know what Z-Wave was. She didn't know what LoRa was. So very much brand recognition that Bluetooth has done a really great job of doing. So great for us to see Bluetooth in all sorts of devices because people know what Bluetooth is all about and they think they understand it. That said, Bluetooth Special Interest Group, their design goals intended to be able to make it very inexpensive and easy to implement in that the wireless chipsets and some of the radio antennas can be the same and or reusing some of the same feature sets of Bluetooth Classic from a hardware perspective, so making it less expensive to deploy and a smaller scale in something like a mobile phone or even in these small embedded battery-powered devices. So why another Bluetooth technology? Well, the evolution in the way that we are using wireless technologies, Bluetooth Special Interest Groups saw that and realized that the classic stack was quite heavy with doing its frequency hopping spread spectrum, and the stack was very heavy, very power hungry. Think about your little headsets. How often do you have to charge the batteries in your Bluetooth headsets? Maybe once a day. They wanted something that would be easier to use, lighter weight on the RF, so that they could use coin cell batteries to be able to power it over a long period of time. The usage that they saw for something like Bluetooth Low Energy was limited bandwidth along the lines of Zigbee and Z-Wave. So AMP didn't make a lot of sense. That was just too much bandwidth to remain competitive. And they really wanted to compete with Zigbee and Z-Wave, yet being able to do bidirectional data transfer, something like NFC, but at longer than 1 or 2 inches. Some of their design goals and where Bluetooth Low Energy excels uses some of the power of Bluetooth in fashion similar to Zigbee, in that low power, low complexity for the stack, the ability to do aggressive power conservation so that you can use a small battery for a very long period of time over decent distances, and potentially distances even greater than Bluetooth Classic. And they wanted to have a very inexpensive radio. Their original design goals with Bluetooth Classic was that the radio chipset they wanted to have cost no more than $5. Their design goals for low energy, if you want to put Bluetooth Low Energy in your device, they want the radio chipset to cost no more than $1. This is really attractive for folks doing hardware development of, hey, we can have this radio communication that runs on a battery and it's super cheap to implement. It's even cheaper than Bluetooth Classic and Zigbee and Z-Wave. So capture the market with brand recognition, making their devices affordable and easy to use. All right, so let's examine some of the changes that Bluetooth Low Energy Special Interest Group made with Bluetooth Low Energy over Classic. Many of the concepts are similar, but have in some cases been reimagined to be easier to use, easier to implement, and easier to understand. Unfortunately, because some of these components are now easier and easier to understand and more simple, we've removed some of the complexity that was some added security features, security through obscurity with Classic. So these changes have definitely, in my opinion, changed the security landscape from Bluetooth Classic to Bluetooth Low Energy. One of the first changes is they changed the way they do channel hopping and advertisement, discoverable mode. With Bluetooth Classic, 79 channels, 1,600 times a second, unpredictable pattern based on each device's unique BD adder. With Bluetooth and only discoverable when in a specific mode and specific frames were being sent. With Bluetooth Low Energy, they've simplified the channel hopping. They've reduced the number of channels from 79 to 37, with 3 advertising channels for a total of 40. So half the number of channels from Bluetooth Classic. 37 channels for data, and 3 channels for doing advertisements. Data, 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 hey, I'm here. Data, 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 hey, I'm here. Always announcing its presence, always in discoverable mode on those 3 channels. And instead of using a unique channel hopping pattern per device, they have predictable, well-defined channel hopping patterns. Mod 37. So if we know where a channel has hopped, say on a beacon channel, hey, I'm here, we know that the next channel will be mod 37, 37 away from its last. We can now hop there and see traffic. And next time it's on an advertising channel, we know that it's 37 steps away from the last one wrapping around. So instead of having to guess and knowing the BD adder, we just listen on one of those channels and we know where the next hop is going to be because it has predictable hopping channel hopping pattern. It was a secret with Bluetooth Classic. It is now no longer a secret. With Bluetooth Classic, it was difficult for us to sniff Bluetooth, because we had to, if we didn't know the channel hopping pattern, we had to sniff the entire 2.4 gigahertz spectrum, 80 megahertz wide. And many of our software-defined radios, unless you're spending several thousands of dollars, will not capture all 80 megahertz. And then the amount of data that you have to capture, it's gigabits per second, hundreds of meg per second to capture all of that, because you don't know where the channel hopping is. Now you do. So if you know, you just hop to the next one and you capture your data. So it's very easy for us to do Bluetooth low energy sniffing. We changed pairing. We use similar methodologies to Classic to use some pins and to derive link keys. However, in standard operation for Bluetooth low energy, the pairing does not retain the keys between sessions. So when I fire up my Bluetooth low energy TENS unit and I use my app to control it, put in a pin, control, it disconnects, throws the keys away. Next time I want to control it, I want to turn the volume down, it has to reconnect, pin, and do that all over again. This becomes an issue for usability in that I set the volume, oh man, that's too much. It disconnects, throws away the keys. I need to turn it down. So I turn it down and it says, oh, sorry, you need to enter your PIN. Every time I want to do an operation, it disconnects. I need to re-enter a PIN to reestablish keys. No, that's awful. So with the pairing operation, they are typically using fixed pins of all zeros in a mode known as just works. Just works always uses a pin of all zeros, and it does all that key renegotiation like that and just uses that default pin. Many Bluetooth low energy devices I'm finding are using just works because it's easy. Because Bluetooth low energy by default does not retain the keys like Bluetooth Classic does. It recalculates them at every connection. Okay. We can have it retain those keys by doing what Bluetooth low energy refers to as bonding. Bonding is more of what we consider the pairing operation with Bluetooth Classic. It does retain those keys. The user enters a PIN, retains those keys, and keeps them over a period of time. Okay. We don't see a lot of devices doing bonding, although I'm starting to see a few that are. There's one example of a device that we'll talk about that I've now seen actually do some bonding, which is good. We talked about profiles with Bluetooth Classic. Bluetooth Classic profiles defined their own data exchange on their own for each individual profile and how they were going to use the data. This meant we had to, within the stack, had to have like 8 or 10 or 12, however many profiles there were, processing methods for that data. Made the stack larger because they had to have that much more, that many more decision trees for what data we were going to decode. With Bluetooth Low Energy, we leverage the GATT protocol for data exchange, which has a very specific format for that data and a structured approach to that data for every profile. So we now don't have to do 12 independent decoding of, depending on the profile, we have one decoding method for every profile and very structured approach to how that data is interpreted. So smaller overhead, easier to use. We don't need to know how to program in 3 different protocols. We need to know how to program in 1. So taking a look at the stack for that, we are separated by the HCI layer, just like we were with Classic. But the big one is that we've replaced the RFCOM data transfer method, which can have various implementations for its data depending on the profile, and that we are replacing that with a standards-based single data formatting method with GAT ATT. All right, so how does, I've sort of already indicated some of these things. How do these changes affect the security of Bluetooth Low Energy over Bluetooth Classic? It's very easy for us to discover devices because they're always beaconing, they're always in discoverable mode on one of 3 channels. And then when we observe them on the channel, they have predictable channel hopping patterns, meaning we can follow along and sniff traffic very easily because we know what the next steps are. If we do that in an environment where they're doing pins or even bonding with retaining those keys, we can capture that operation very easily as opposed to having to capture the entire swath with several $1,000s worth of software-defined radio. Pairing options are limited. Certainly, the most common method is to use either just works or pin with a non-fixed pin. But pairing with a non-fixed pin is a nightmare because you have to keep re-entering that pin for every operation. So many of the devices that I've encountered are all using just works with static fixed pins of all zeros. Every device. I think of the devices that I've encountered, I've seen 1 or 2 that have used bonding operations with non-fixed pins. Everything else is just works, which is terrifying. And as a result, because of the pin just works, many of the profiles are considered mode 1 being open. While they are using a pin and are potentially doing some encryption, we know the pin, so they might as well be able to be connected for every device. So once we can connect with just works, we have full reign of the device. So it's effectively becoming mode 1 with just works. As a result, we can then start querying these devices once we're paired with them using just works and can write to and read from the various components of the data. The problem now becomes is the data encryption of the device that we're potentially interacting with. While it may be encrypted over the air, we need to have some potentially encrypted in rest. Like this is using HTTPS over WPA, WPA2. So we're left up to the manufacturer to figure out how they want to use that data and whether they want to encrypt it or not. While doing the discovery for this class, I was looking at some of the devices that we wanted to have you interact with. And we went through a couple of iterations and then loaner devices, and I thought I found one. I thought I had found one in that I was at my local Home Depot and there's a Fiat Electric, F-E-I-T. They had a Bluetooth low energy enabled light bulb. And it was like $3. Oh, well, this is cool because now I can get a little like 70-cent adapter to screw the light bulb in and plug it in. And now you guys all have Bluetooth light bulbs you can interact with. This will be great. And a $3 light bulb, they're not going to have any security on this. I was wrong. That's wrong. It did use just works, so I could use my app to pair with it. It did use a pin, and it did bonding operations. That was my first disappointment. But even still, we could use a pin and bond with it and start interacting with the bulb. And I was reading values, and I would change stuff in the app, and I would read the values, and they weren't anything that I could discern. So I'm like, how the heck are they doing this? They're doing some security implementation by encrypting that traffic that they're storing and sending to the bulbs to change the on-off state. It was just a white bulb on-off. And I couldn't figure it out. So I'm like, how the heck are they doing that? So I Googled, and I found that there was a GitHub repository that had someone that had reverse engineered the Android app to see how they were encoding the data. And it was something ridiculous in that they took the pin and they combined it with this string, and then they took the reverse byte order of that string and took the middle 8 bytes, and then they reverse ordered that, and then they hashed it with the timestamp of Julius Caesar's birthday. And I'm being a little bit facetious here, but it is still very similar to this type of thing. And then they took that output hash and they split it in the middle and they swapped ends, and then they reversed it, and then they took the last 8 bytes and the first 2 bytes and swapped those. I'm like, what are you doing? But someone reverse engineered the Android app to figure out all of those mechanisms. And then they could reverse it, and then you could change your settings and you could control it with your own stuff as opposed to the app. Like, well, that's kind of neat that you went through all that work, but to what end? So looking at these profiles, each one of the components that we may want to interact with is going to be using GAT ATT service. And each one of these profiles will have some data that is useful to how we're going to interact with these devices. And it will expose that via GAT ATT, which has a hierarchical fashion of data structure. So the GAT server is going to handle all of the interaction with that data, and then we just put data in those various fields. We have some hierarchical fashion for us to interact with those profiles. We have a service, or in fact, multiple services. Each one of those services has one or more characteristics, and then each of those characteristics has some data assigned to it or a descriptor. So hierarchical fashion, we have a service, characteristic, and a descriptor. Let's look at that a little bit more in depth and sort of see how that lays out, and I'll give you a good example. Okay. So each one of these characteristic has several possible features. We have the ability for it to be read-only, write-only, read-write, and read-notify. And I think there's one other. Read-notify, I think, is pretty interesting in that, let's say we want to do temperature monitoring. Read-notify is acting as a subscription-based service. We pair the devices, we join the devices, they're communicating, and we want to do temperature monitoring sort of real time. And if the temperature is at 71 degrees Fahrenheit, we read 71 degrees, 71 degrees, 71 degrees, 71 degrees, and we keep reading that every 3 seconds. 71 degrees. We're consuming power for both of those radios. And what if it's a battery-based sensor? Battery starts depleting. But nothing has changed. 71, 71, 71, 71, 71. We want to do something when the temperature changes. So read notify is a read 71 degrees, tell me when it changes. 71, 71. We're not reading, we're just waiting. It still says 71. And then, boom, oh hey, it just went down to 70. So we'll do like a push notification over Bluetooth Low Energy to our mechanism over the GAT server. So we're saving battery power. We don't have to keep reading and have it be the same value, just notify when something changes. So taking a look at that visually and breaking this down, let's take the more advanced $5 Fiat electric light bulb that you can turn it on and off with the app, and you can change the colors. Let's take a look at this. So we have two services. We have the power service and the color service. Within the power service, we have a characteristic, power state, on or off. The descriptor is a data value, 1 or 0. We write a 1 to this descriptor for the power characteristic for the power service, the state service. We write a 1 there and it turns the bulb on. We write a 0, it turns the bulb off. We haven't changed color. So this service would be the color service, and we have two different characteristics. Hue, brightness. The hue service, we give it a value between 1 and 255 from yellow, red, orange, green, blue, yellow, indigo, violet, so forth and so on. And then how bright is it? Do we want it to be a muted or do we want it to be an intense? We change both of these values and it will make it either more intense or change the color. So hierarchical fashion for some of this data. In order to start interacting with Bluetooth Low Energy, we need some hardware and some software. Okay. We need to be able to do some sniffing potentially. We maybe want to use JustWorks and connect to the device and read services, characters, and descriptors and maybe manipulate those values. So connect to the device and see what we can do. And are they doing any encryption? Okay. And then obviously we need some devices to evaluate. This is the fun part. Go to Amazon and search for Bluetooth Low Energy. Bluetooth Low Energy in everything. I picked up a bear that dances. It has Bluetooth Low Energy in it. It has an app. I don't know why I bought this, but I did. I have a set of Christmas lights in my office that are Bluetooth Low Energy enabled. Use an app, change the Christmas light hue and speed and which way they move, and all sorts of stuff has Bluetooth Low Energy. We also need some software to potentially interact with the GAT server, perform sniffing, fuzzing, you name it. And we have all sorts of various solutions for Linux, Android, and iOS. So some of the hardware tools. One of the more robust tools for us to do interaction with Bluetooth Low Energy and Bluetooth Classic and Wi-Fi and doing HCI decoding and HCI interaction for all of these is the Alesis Bluetooth Explorer. Josh was lucky enough to be able to use one of these as writing some of his books, and they loaned it to him. They said, hey, I'm writing a book. Apparently that's all it takes for them to send you one of these. It was a loaner. He had to send it back. They have some amazing proprietary software for use with this. It's effectively a software-defined radio designed for capturing the entire band and being able to decipher all of the various protocols. It is expensive. It's about $30,000 US. My chief financial officer says that will not give me approval to purchase one of these. And by chief financial officer, I mean my wife. Right? She says, you have 2 kids to put through college. You could probably spend that money more wisely. She's right. So, while this may be best of the best, we could certainly, consider, a $5,000 software-defined radio, but without the advents of Alesis' really, really nice software, we're left to do a lot of that ourselves or find other projects that have had it happen. Kane's shaking his head. Yeah. Worth the money if this is what you're going to be doing all the time. Taking a look at some of their software, being able to dig into all of the commands, doing all the decodes of their packets, and looking at they're doing an ATT write between source and destination, and eventually contents of those packets as well. So pretty neat stuff. There's a bunch of other hardware options as well. The Nordic NRF 51822 come from on boards from Adafruit. She has 2 different versions available at the store, the Sniffer and the Friend. The Friend is intended to be a device for you to implement some Bluetooth Low Energy functions. The Sniffer is flashed with a firmware version for sniffing and doing follow-alongs. They're very inexpensive. You can flash the Friend to be a Sniffer and the Sniffer to be a Friend, but it requires you to have some special hardware to be able to reflash it. It's not reflashable over USB. Just get one of each or get 2 Sniffers because they are relatively inexpensive. That is not $30,000. Okay, it's $25,000. Readily available from both Amazon and Adafruit website. And we can directly use this device to capture packets into Wireshark. We have some apps to pull them both on Mac OS and Windows to capture to PCAP, or we can feed it directly into Wireshark with a named pipe. And there's also some Python bindings so that we can query the device with Python to do all of that same functionality ourselves if we so choose to. So using the Windows app for the BLE Sniffer goes and discovers devices that are broadcasting. And then we tell it which device that we want to sniff traffic from, because it will go do the follow along because it has that predictable channel hopping pattern. And then we can pipe that directly to Wireshark. In this case, we have a received handle value notification. This looks like it was a push from a read notify operation. It was a, if I remember correctly, it is a notify using the ATT protocol. And we have a value that we have the handle that sent the data, and that now the value is 54. What that value is, what the device is, I have no idea. But we can now get that in plain text. And whether or not they're doing anything with that, like they were with the Fiat light bulbs, that is now left up to us to explore. Some ways in which we can start doing some analysis of the data to figure out which services, characteristics, and descriptors may be of interest to us for interacting with the device is to use the app or use the device as intended and observe the commands that are being sent when you use the app itself. But instead of sniffing them out of the air, let's capture them locally from a device as intended. When I press the power button in the app, it's being sent from the app to the Bluetooth Low Energy stack and out the device. Let's see what the app is sending to the Bluetooth Low Energy stack and recover that, so I know when I press the button, it's always sending this service, this characteristic, and a 1 or a 0 to the descriptor to turn it on or off. In order to do so on Android, we can enable HCI snooping for Bluetooth and Bluetooth Low Energy. So we'll capture all of those commands that we're sending to the HCI layer to get turned into packets. It will do packet capture on our Android device of the commands we're using from our mobile app. And then we'll store those onto the SD card or the internal simulated SD card. We take that log file over to our Linux system and post-process that and examine those logs, because it is using standards-based tools on both Android and Linux that are compatible. Once we can inspect that data, we can see what characteristic services and descriptors are being used and what values are being sent. So now maybe we can connect to it and interact with that service character and send those same values to that descriptor and see what happens. Do they change every time, or do they not change every time? They're using BTMon for HCI snooping on Android. BTMon also exists on Linux. So we can capture the log on our Android device, move it to Linux, and then use BTMon to look at those logs as well. We can also use BTMon under Linux to do the same sort of captures into PCAP format. If we run it without the PCAP, it will output text to the screen. In this one, it's finding BTMon under Linux, the same backend as used under Android. It is finding that there's a device advertising on one of the advertising channels, and the name is Light Show Strings. These are the Christmas lights in my office. And then we can do a capture to PCAP as well. How can we start doing some additional sniffing? Again, back to the Ubertooth one, there is a Bluetooth Low Energy tool chain within the software applications. It is still being worked on. It's not always there. It requires a firmware update to take advantage of most of this stuff. And I just saw that there was a firmware update fairly recently to improve some of the Bluetooth Low Energy functions. Readily available from all over the place. And the applications within the Bluetooth Low Energy toolchain for the Ubertooth software does give us the ability to do custom packet sniffing and injection, all the way down to the physical layer. We can do some sniffing and follow along with the Ubertooth one using Ubertooth BTLE, Bluetooth Low Energy. Bluetooth Low Energy is Bluetooth 4, BLE or LE or BTLE. It's all the same thing. They couldn't figure out what they wanted to call it. Bluetooth did a really bad job at managing this, and now they have a set of standards. And in this case, we're doing Bluetooth Low Energy and promiscuous mode, and follow. So capture everything. When you find a device, follow it along. Spits a bunch of information out to the screen for us and gives us some addresses and which frequency it observed that on. And the second half, we're doing the same command, but instead of writing it to the screen, to libpcap formatted file for later analysis. We've captured some packets. We can see the data. We can see which services, characteristics, and descriptors are being written to and what values are being written to by either HCI snooping or capturing stuff out of the air, sniffing. And hey, we did that with a very inexpensive device, $25 as opposed to something like Bluetooth Classic, several $1,000s, or not being able to follow along with the Ubertooth 1. Significantly easy for us to capture traffic and analyze it with low energy. Now we have that traffic and we've analyzed it and seen some potential areas in which we aim on to explore and see if we can interact with when the user doesn't expect it. We need to connect to those devices ourselves. So let's use some standard Bluetooth low energy adapters to try to connect to the devices, see which pin settings that they use. Let's use JustWorks. Can we update services, descriptors, and characteristics to perform undesirable results on the device? Can we fuzz the device to discover undocumented characteristics that aren't used in the app that maybe make the battery catch on fire? All sorts of fun things. For doing that direct interaction, we just need a Bluetooth low energy dongle. And guess what? You got one at class 1 for really long distances. So the Perennisena UD100 does support Bluetooth low energy. All right, let's take a look at some of the tools for, software tools for interacting directly with our Bluetooth low energy devices. One of the first and some of the built-in tools, we can use HCI tool and GAT tool. And I was told by James Lee Vidal, one of the other instructors and the other courseware author, that the Blues application suite was going to start deprecating these tools. And in the most recent version, you had to add a command line flag to make sure they were built. And I went and did it and didn't add the command line flag, and the tools were still available. So I don't know. But then again, I don't know what the replacement for those is going to be either. So either way, they are still there. They're still available for us on RVM, and they're quite effective at doing some initial exploration. Specifically, HCI tool from doing some command line scanning for discovery of low energy devices. And then once we've discovered devices, using GAT tool to do service discovery, value queries, and even read and write to the different values as well. And it is, we're going to use it in interactive mode, but you can specify all of the things that we do in interactive mode from the command line, so it's possible to script for discovery and fuzzing. There are tons and tons of tools for working with Bluetooth low energy because it is in fact so easy for us to interact with, and we don't need really specialized hardware, and the security is, in my opinion, pretty poor, so there are lots of things for us to do and lots of tools. So we're going to cover a couple, and some of the ones that I've had really good luck using. So discovering devices with HCI tool and the LE scan command, it goes and starts scrolling by because the devices are always advertising on one of those 3 channels. So we get lots of advertisements, and it will find them and then find some additional information about them. For example, a couple in my office, the light show strings and the Pavlok. Looking at the devices, we've got some available. Let's go connect one, and then using GAT tool to connect to a specific device. We're using it to connect to the Pavlok in interactive mode, the -I. So it gives us a prompt. Doesn't actually connect to the device until we tell it to. Tell it to connect, and then it gives us some indication that it has connected. And then we ask the device about its primary services. With primary, hey, tell me about all the services that you have, and it gives us a big list of a bunch of services. So it tells us about this one attribute, and it has a bunch of handles. So this is a service, and it's got unique identifiers for each one of the devices. So we have a service between 1 and 7 with a unique UUID. And this is a group. So we now have a bunch of characteristics and descriptors within that group. So we can reference group items and we can reference things individually. So taking a look at 07 through FF, tell me everything about the values from 7 to FF. And it came back with a whole bunch of handles available for a bunch of characteristics with unique identifiers as well. For that final characteristic, picked one at random. I have no idea what any of these do, and tried to read the value from it. And sure enough, I was able to read from that individual characteristic to receive the descriptor, the data stored there in that characteristic for that individual service, and then tried to write to it. And unfortunately, in this case, the write failed. And for me, this is one of those troubleshooting steps that's kind of stinks about GATTool, because when we go query for the services, it doesn't easily, and I haven't found a way for it to tell me which services are read, write, read, notify, you name it. So we have to experiment with stuff. There are other tools out there that will give us some indication as to the state of those individual characteristics, whether or not they can be written to, and so forth. Some other ones too is the service identifiers are given to us as a string. However, the Bluetooth Special Interest Group has a set of mappings for those UUIDs and those individual identifiers. That they have some that are specifically defined for specific services, such as the name, the battery state, the type of device, and they have some fixed values. And then they have a bunch that are considered user-defined. And those user-defined are really where all the good stuff is that we may want to modify to interact with the device. So it doesn't do the mapping to the special interest groups lists for describing what those fixed characteristics and services are. There's another tool that I enjoy using, the NRF Connect mobile utility on either iOS or Android. And they just redid the app. So all of the screenshots are now different. NRF Connect from Nordic Semiconductor does really great on Bluetooth low energy exploration. And I like it because not only can I do the same thing I could do with HCI tool and GATTool from the command line, I can do it from wherever with my device. I can read, write, and it will also tell me the status of those services, whether they're writable, whether they're readable, or whether they are push notify, and allows me to interact with them as well. I have found that the Android and iOS versions are not equal in that I was doing some testing for a device manufacturer that was manufacturing door locks for hotel use. And they had Bluetooth low energy available and some other connectivity types on the locks. They hadn't yet offered them for sale. It was pre-sales testing. And we started interacting with the Bluetooth low energy portion. And what we found was that if I paired my phone with a Bluetooth low energy lock, no one else, or if I attempted to connect and I was connecting to the lock and was trying to interact with the lock, no one else could connect to it either because it didn't support multi-tenancy, didn't support concurrency. So one user at a time. So there was a denial of service condition there. So take my phone connected to door lock number 1, take another phone connected to door lock number 2, and I needed another phone, so I grabbed my Android phone off of the shelf installed the NRF app, connected to the second door lock, and then got my wife to try to interact with either one of them, and she couldn't. And then I realized that within the Android version of the app, you can create multiple tabs and connect to multiple devices from the same application. You couldn't do that on iOS. So now, thinking about that sort of attack scenario, I could take one Android phone and tuck it in the ceiling somewhere and just have it connect to every door lock on the floor, and then nobody can get in their rooms because they can't unlock them over BLE. Now, they had some other fail-safes to be able to have other ways of opening the door, such as NFC, and they had keys and those types of things. So, but we could deny service to the low-energy stuff because one user at a time. All right, so I haven't done this, so let's see how this goes. Nope. And I will, of course, this will be when I get text messages from my wife, and, right? All right, so starts up, does some scanning. Let's even make this a little brighter. Oh, too bright. All right, it found a bunch of devices. There was a GoPro there earlier. Some of you getting your TENS devices turned on. Huh. All right, there's lots of Bluetooth low energy stuff in here. Wow. Wow. All right, let's try this one. Advertisement data. Okay. How about this one? Connecting. All right, one of them doesn't like me to connect, apparently. All right. Let's try this one again. Does not have any advertised services. Doesn't like to connect to the tile. Oh, it did connect. And we've got some services. All right, let's connect to somebody's TENS unit. I know I'm being bad. I'm connected to someone's TENS unit that now they can't connect to it either. I'll make sure that I disconnect. All right, so a bunch of services. That's kind of hard to see. Let's do this. All right, so this one actually tells us what we're looking at for some of the services, and unknown characteristic here, read, write, notify. Let's read from it. We can write some values. Hooray. So we can interact with the devices from mobile. There was a lot of devices there. That's terrifying. That was kind of terrifying. Okay, so the older version of Nordic NRF Connect. Well, we did a little demo live with the new version because these screenshots are a little bit out of date. The new one is pretty robust. I think I might have liked the old interface a little bit better. No swiping and all this type of stuff. All right, so we did similar types of things. We inspected some of the characteristics. We looked at the services. We could see that some of them, they were telling us whether they were read, write, notify, read, write, you name it. And then we actually wrote a command to one of those devices. Sorry if that was your TENS unit. I apologize. I don't know whose it was. Okay, and I'll make sure I go turn off my Bluetooth radio so that it physically disconnects from that and I'm not locking you out.
BLE suite from the NCC group. Their suite has a couple of different components written in Python so that we can use Python to interact directly with some Bluetooth low energy stuff. And they have a wrapper, a CLI wrapper for the BLE suite Python implementation. And they have the ability to do BLE replay. Absolutely cool stuff, but not for the faint of heart. If you don't have any good programming skills, it may be difficult for us to use. But because of the power of Python, we learned with some Scapy stuff yesterday, we may have the ability to do some really, really good fuzzing using Python for that. In this case, using the BLE Suite runner or the CLI interface for their Python libraries, we can have it start doing some discovery and interaction with BLE Suite. All right, if we can capture traffic, we can follow along, we can potentially capture pairing requests, just works, or even bonding requests, just like we thought we could do with Bluetooth Classic. However, significantly easier with Bluetooth low energy because predictable channel hopping patterns, we can move around and follow them and observe all of these connections and grab all of the same portions of the data in the air, including the addresses, identical to the Bluetooth Classic type of exchange. If we have all that information, we can do offline brute force attacks to recover the PIN. Okay. We can then retrieve the temporal key or the PIN, the TK, for those with brute force, just like we did with Classic. The big thing here is it's a heck of a lot easier for us to follow along those connections to observe those pairing and or bonding attacks. Okay. We can use a bunch of different tools, including Bluetooth Low Energy for Ubertooth with Ubertooth BTLE. Follow on this connections, write them to PCAP, and then use some tools to capture that captured session to be able to do pin cracking with a tool called Crackle. Much like Bluetooth Classic, link management protocol is still in use in same ways, and we could in fact issue LMP not accepted, claimant has no link key, to force repairing and or rebonding operations and capture that as well. Unfortunately, the author of Crackle, his name is escaping me at the moment, but he's the one that is responsible for the Ubertooth BTLE software tree, has been trying for a long time to be able to craft those messages accurately and has not had much success in doing so. Mike Ryan. And I actually, Josh and I reached out to Mike Ryan, I want to say about 6 months ago to see what his status was. And his answer was, wow, I haven't looked at Bluetooth Low Energy in so long. I've even forgotten I needed to do that. So maybe we spurred something in him and he'll get those deauths with those LMP not accepted messages. So once we grab some packets, we'll use Ubertooth BTLE. We'll go into promiscuous mode and do follow along and write to PCAP with -C. Once we feel we've got enough packets and or feel we've observed a pairing operation or a bonding operation, we can pass that packet capture to Crackle with the -I and then a -O for an outbound, because if it does recover the key, it will then decrypt all of the encrypted packets outbound for us. Super simple. And in this case, it found the PIN or the temporal key, the TK, of 6 zeros. Or, as Mike Ryan puts it, it's the just cracks or just works. So it was a pairing request based on default pins, the typical scenario we see for Bluetooth Low Energy. So this one was super easy in that the pairing operation was all zeros. So super easy here. All right, we can do this with other stuff. Typically, we're going to find just works. However, if we're seeing bonding operations where they retain the key, they're typically not going to be using the just works, or as Mike Ryan puts it, the just cracks pin. And these are subject to the same challenges that we have with Bluetooth Classic, in that there are potentially few and far between opportunities for us to catch the pairing sessions. So we have to time that just right. Again, like sitting at the Panera Bread next to the local AT&T store. We could potentially do deauthentication attacks, and Mike Ryan had been allegedly trying to do that by creating our own device with the Ubertooth and spoofing the BDAdder or the master and sending deauths LMP not acceptant to force a repair. But again, largely academic exercise on that particular one. So thinking about those kind of challenges, we're talking to you folks about it. We've included it in the course. You guys get some really great ideas, and some of you are really smart and may actually go see if you can go implement this yourself. Also, because we've tickled Mike Ryan about this idea again, maybe he'll pick it back up depending on where he finds some time to make that happen. We could always potentially do RF jamming, but again, we talked about the legality there as well. So it really becomes hard for capturing that pairing and or bonding session if we're not using JustWorks. Limited time-based opportunities. Some other things that we can do would be fuzzing. And specifically here for fuzzing, fuzzing above the HCI layer, interacting with GAT ATT for their characteristics and services, similar to like Bluetooth Smasher did, with interacting with the various profiles and sending erroneous data or unexpected data there. My thing that I'm thinking about here is that if I capture HCI logs with an application and it interacts with 3 sets of services, and I fuzz and I find a total of 7 services, well, what are those other 7 services that are never referenced by the app supposed to do? Is it there for future use? Is it there for some other implementation in maybe a pro version, different software? And if I can interact with those, what happens to my device there? So some undocumented services. Explore some of the security using the different pins and so forth. And then what happens if we find those services or documented services and we send all sorts of values that they don't expect? Similar to what we were talking about with fuzzing Wi-Fi. There aren't a lot of automated tools. We could potentially script a bunch with the Blues tools or use BLE Suite and some of those types of things. Scapy has the ability to do packet crafting, but I cannot find any documentation on Scapy's Bluetooth low energy stuff. I've searched and I've searched and I can't find any good documentation or good examples for constructing Bluetooth low energy packets. So it's an option, but with someone with potentially a little bit of time. Thinking about finding some of those undocumented services, we're actually interacting with the GAT ATT service, so we're not bound by issues with the HCI layer, and we have Python libraries and other tools to be able to make that happen. BLE Fuzzer is an option for us, doing a little bit of automation using Blues utilities, and the BLE Suite stuff in Python gives us the ability to do create our own fuzzers there as well. This particular set of tools has been deprecated. It is available and it works really well. Bleh is a set of ATT fuzzing for Bluetooth low energy. It will find devices, it will do advertisement discovery, it will automatically do the translation of BDAdders to manufacturers and the services to the Bluetooth special interest groups mapping and give us friendly names there, tells us whether we can connect to it or not. We can then use the tool to actually connect to it and do handle service and characteristic discovery. We can use it to write to the device, and it's all pretty easy to use and has some decent curses-based output. However, Bleh has been deprecated, it's still available and still usable, but the author has moved all of the functionality to another tool with BetterCap, and BetterCap is just freaking amazing. Still taking a look at Blair, doing some discovery there with T0, so continuous discovery. And in this case, we found a device that allows connection, but wasn't able to determine the vendor here. So I did a Control-C so that it wouldn't keep scanning for multiple devices. In this case, we can use BLE to interact with an individual device and do service characteristic and descriptor enumerations with the -E. So it goes through everything it can discover and grabs all of the individual items and the value there. And in this case, we were interacting with my wife's Fitbit 1. Once we knew some services, characteristics, descriptors, we can also use BLE to also interact directly with the device for our characteristics and attempt to update some of the information. Okay. And in this case, I attempted to change the name, if I remember correctly, BA. No, some unknown descriptors here that had a write capability to see if I could update whatever was there. I don't know what it did, and I don't know what that individual characteristic did. So, but we're able to use it to send some stuff. BetterCap, where all this stuff has been moved to, is very similar in its output and some of its mechanism, but with a lot more capabilities and is under active development. And yeah, these are the colors from the tool output. So start BetterCap with sudo on Kali. It would work just fine because you're as root. And we are going to give it some commands to evaluate when we start it up. And in this case, we're giving an eval of ble-recon.on, and it will automatically use our first Bluetooth low energy device. Starts up BetterCap, and it starts finding new stuff in the environment automatically and starts giving us some notification back. ble.show will give us a list of all the Bluetooth low energy devices that it's discovered and the information it's been able to. Looks very similar to the stuff out of BLE. And in this case, it discovered my LG new flat screen television that my wife wasn't particularly happy that I bought because she was away for 3 weeks in Australia and I was home with the kids. So while the cat's away, the mice will play, right? Yeah, I went and bought a new TV. Looking at that, we can also do that same enumeration just like we did with BLE. We had a discovered device for the MAC address, and we can do ble.enum for that device, and it will enumerate all the things. Find all the services, characteristics, descriptors, and tell us the data there, as well as what type of properties it has, read, write, notify. Now these had a little bit more stuff available, but I trimmed the output so that we could fit it on one slide as opposed to 30. We can also use BetterCap to write values to those particular items, and attempted to see if I could write a specific value to 2A 8B for that handle. And I don't know whether it ever did, but we can use the same tool as well. Okay. Neat stuff with BetterCap, and love that BetterCap is under constant development. I was having issues with it and saw that there were already some issues open for the same thing as I was experiencing. And within a day or so, was it Simon Margatelli fixed all the issues under constant development, and neat stuff. Replay might be an interesting attack. When we were talking about Zigbee yesterday, if we could capture some commands for Zigbee, say for that spill gate on a dam, and then replay it later, Wouldn't that be neat if we could do that with Bluetooth Low Energy? So take the spill gate when it opens 1 degree and replay it 99 more or 90 more times, 89 more times, and have that dam open. Might be interesting here as well, how we're starting to see Bluetooth Low Energy used. What happens if we pull up in front of our friend's house and we observe them use their phone to interact with a Bluetooth Low Energy door lock on their house, and we capture that transmission to the door lock, unlocks their house, and then they go on vacation a week later and I show back up to their house and replay that same command later to unlock their house. That could be kind of interesting. I can see the value in that attack. BLE Suite has the ability to perform Bluetooth Low Energy replay to potentially perform that type of attack. I haven't had much luck making it work, but maybe I need to try harder. Maybe there were some bugs and there's some newer updates to it. There's also the option for us to do Bluetooth Low Energy man in the middle. Get the mobile app or the device to connect to us instead and act as a proxy. Make it think it's connecting to the real device. It sends a command to turn the light bulb blue. We intercept that command and say, yeah, don't turn it blue, turn it yellow. And the device thinks it received the valid connection from the command, from what it thinks is the actual device. So if we can capture that, we can also potentially replay it multiple times through something like that, as effectively acting as a GAT proxy. Unfortunately, it's not terribly easy to do, but it is possible. We need 2 Bluetooth Low Energy adapters, one to lure the client to think it's connecting to the real device, and the other one to connect to the device thinking it is the real device. And there is a tool that was released at DEF CON, not last year, the year before, called Beetlejuice. So Beetlejuice takes 2 Bluetooth Low Energy adapters and allows us to perform a man-in-the-middle proxy. So it requires 2 different interfaces, and we relay through the virtual machine to a host machine via IP. So we run Beetlejuice proxy in, say, our virtual machine, and then we run Beetlejuice-U and send it to our virtual machine on our host. And then navigate to the web interface in .3, and then we start attempting to spoof the 2 devices, the client and the device. In this case, selecting a target device that we want to proxify, and then perform intercept and replay. And when we do the intercept, we get some data and can form a replay. We can replay the initial value that was sent through the proxy, or we could even change those values as well. We've seen a couple of security enhancements. We saw some security issues, in my opinion, with some additional sort of non-standard type of implementations for security for Bluetooth Low Energy. The first one, pairing. Most of them are seeing that with just works, and as we've discussed, dropping all of those keys every time they disconnect. However, bonding is very similar to that of the Bluetooth Classic pairing, in that it does retain those keys. And most of the time, I've not seen one that uses the default keys. You're actually having some user interaction there. And also some MAC address restrictions. We can be using the public address or a randomized address for doing some connections. And some devices will not allow you to connect if you're using the public address. They'll only accept random ones. And some devices will only allow you to connect if you're using a public address and not a random one. But you try to do the connection with a random address and it fails, so you try a public one, and it works. You have a 50-50 shot. So I don't really see where the security benefit here is, aside from having me run the same command twice. So that is one of the things that they attempted to use as a security feature, but I don't see it doing so well. How about Bluetooth 5? Bluetooth Low Energy as Bluetooth 4. Bluetooth 5 is an evolution of Bluetooth Low Energy with an intent to further target industrial IoT and IoT as well. The big one differentiators with Bluetooth 5 is the increase in distance or the increase in speed from 1 meg to 2 meg or from 100 meters to 200 meters, but not both at the same time. Pick one. You can either get increased speed or you can get increased distance. They increase the size of the packet. They increase the size of the beacon to include more information, and you can now do chained beacons, so like you can fragment your beacon to include even more information. So instead of beaconing saying, hey, I'm a Bluetooth Low Energy device, I'm a printer, you can say, hey, I'm a Bluetooth Low Energy device and I'm a printer, and I have 30 sheets of paper in tray number 1, to be continued. Next beacon, hey, I'm that same printer and I have 50 sheets of legal paper in tray number 7, to be continued. Hey, my black ink level is at 50%, my yellow is at 17, and you should probably consider changing the magenta ink pretty soon. So we haven't even connected to the device and it's beaconing saying all this information. What could possibly go wrong? Okay, and potentially at significantly further distance. Okay. Some other design goals with some very aggressive power saving, battery life up to 10 years, and does require new radios to be able to interact with Bluetooth 5. However, most of our modern mobile devices already have these radio chipsets for us to be able to interact with them. Okay. I haven't seen a lot of Bluetooth low and Bluetooth 5 stuff yet. Obviously, it's in the phone. I haven't seen a lot of client devices. And again, I think this is further evolution of their technology to continue to supplant Zigbee and Z-Wave. So what are some of the practical benefits of Bluetooth 5? Larger packet size means that we can deliver larger quantities of data faster, because attempting to do like an over-the-air firmware update on a Bluetooth Low Energy device at 1 meg with itty-bitty packets is painful. Now we have the packet size of the MTU 8 times larger, so makes firmware delivery a little bit easier. The beacons are larger and supports chaining and or fragmentation, so we can include much more information about the device upon discovery. And we have a couple of different modes for backwards compatibility. So in Bluetooth 5, we have LE1M for the 1 megabit service for backwards compatibility to Bluetooth Low Energy. We have LE2M, which increases the speed by changing some of the modulation. And then we have coded LE, which gives us our increased range. And they're achieving that increased range by doing forward error correction on the data. So as we get further away and the signal gets weaker, we're more apt to receive errors. But because of the forward error correction, we're able to recreate the spot where we got errors or missed data. So we can recreate those packets with weaker signal strength at further distances. Some other stuff, they added adaptive frequency hopping into the channel hopping pattern for low energy. Low energy did not have adaptive frequency hopping like we did with Classic. They added it back so that they can potentially avoid Wi-Fi and so forth. The improved range based on the forward error correction and the enhanced advertising with the larger beacon frames. All right, huge adoption in Bluetooth Low Energy. I'm finding all sorts of fun stuff. I'll tell you about my Pavlok that we saw on some of the slides. The protocol is overly simplified from classic, making it a heck of a lot easier for us to find and interact with devices. And as a result, the market for hardware and software tools has exploded. We have all sorts of fun tools under Android, iOS, Linux, Mac OS, you name it, for doing Bluetooth low energy exploration. We talked about pin cracking, men in the middle, and replay and fuzzing tools. And then we did a little summary on Bluetooth 5 when we start to actually see that make it to consumer devices. All right, I'm going to let you guys work on the Attacking Bluetooth Low Energy Lab using your Raspberry Pi. It takes a little bit of time to set up and can take a little bit of time to start figuring out the navigation and actually doing a little bit of the exploration. You are going to be using your Raspberry Pi and you're going to SSH to it just like you did for the fuzzing. You will navigate to a web page on the Raspberry Pi that is simulating a Bluetooth low energy TENS device. And for those of you who may not be familiar with it, TENS is using like electroshock therapy for massage and those types of things. But depending on how far you turn up that volume on the TENS, it can get quite painful and have very interesting results. This Bluetooth TENS device is modeled after an actual Bluetooth TENS device that I purchased off of Amazon, which comes with a mobile app, and it uses Bluetooth low energy to control it. So that takes a little bit of setting up and interaction and those types of things. The other one too is when we go into that lab, your device will be uniquely named. Please only connect to your unique device name because Bluetooth low energy, for the most part, does not support multi-tenancy. Does not support multiple connections. So if you connect to someone else, they can't do their lab because they can't connect to their own stuff. And I'll let you get to that. So taking a look at some software-defined radio and some potential practical application, give you some ideas to what software-defined radio looks like, what we can use it for, and some of the things that folks have already done with it to give us an idea about discovering protocols, how we can use the discovery protocols and the tools that exist to potentially affect some security operations, taking some of those tools and maybe giving them a little different spin for us to do additional things, and really give you an introduction to what software-defined radio can look like. While we could spend a week, 2 weeks going into all of the details of software-defined radio, we really want to give you a taste of the rabbit hole and how deep it can go with some of the type of stuff, and look at just a few things for the types of attacks that we can see across multiple protocols, multiple frequencies, and so forth. So let's take a look at what software-defined radio is, when we may want to consider using it in a penetration test or in some type of radio testing. Taking a look about what type of software-defined radio you may want to use and look at some of the more popular options. Okay? And then look at a couple of projects that already exist for software-defined radio that give us some ideas about what we could potentially do with some of these protocols, how we can potentially change them to do something else, and potentially even some risk to our organization based on some of the things that we find. There's an interesting one. I'll see if I can bring up the article when we get to one of these. The biggest one at the end is, why would we not use an SDR in some of these tests? Because there may be reasons why there are better tools for the job at hand. So what is software-defined radio? By its name, it is a radio defined in software. It is a multi-purpose radio, not defined by or limited by single-purpose hardware. I turn it into a person, and it has no preconceived notion of purpose. It can do multiple things. It can be reprogrammed to do just about anything we can imagine with a radio, and it does not have a fixed purpose. Unlike the AM/FM radio in my truck, that has single purpose, well, two purpose, really. It can demodulate frequency modulated signals, and it can demodulate amplitude modulated signals within specific frequency ranges so that I can listen to AM/FM radio. That's all it can do. With software-defined radio, we can create a radio in software to listen to demodulate FM, to demodulate AM, to listen to demodulate QPSK, to demodulate all of the things, and then apply various decoding to all of those signals for every type, as long as we can imagine and understand how those signals are constructed. It does require potentially a little bit of heavy lifting to do the real-time processing for all of those signals as received. Maybe we're doing it after the fact from disk. And we have a couple of ways in which we can do that. We can directly interact with the radio with some of the platforms, or we can with a, say, quote, standalone program, or we can use a multi-purpose tool such as GNU Radio and or GNU Radio Companion. So we're building radios by dropping blocks in a window, GUI development. So Kane has apparently done a lot of that. So I hope I do this whole section for you justice. All right, software-defined radio is so hugely flexible, but in its huge flexibility, it also requires lots of work for us to put it together because we have to potentially build everything. Now, there's been lots of smart folks that have done lots of building for us already and have shared, so we can often leverage some of that existing work to move forward with some of our projects as well. So thinking about generically what a software-defined radio looks like, we'll have an antenna with an RF radio, RF front end, with those that RF front end tied to some analog to digital converters or digital to analog converters for transmit, tied to some sort of processing, and in the higher end radios with a field programmable gate array, with the ability from that field programmable gate array or some sort of processor to outbound, whether it be USB or Ethernet, to retrieve data as decoded from the RF front end as typically IQ data. So formatted data that we can deal with by knowing the types of formats. We tie that to some PC hardware of some variety, maybe even a Raspberry Pi, some sort of general purpose computing in which we interact with the device with some software for doing receive or transmit, demodulation, decoding, you name it. So a bunch of different parts. And depending on your software-defined radio, this is a generic diagram. We will vary the number of analog to digital and digital to analog converters here. So if we think about our RTL SDR, which is receive only, we will only have an analog to digital converter. We will not have the digital to analog for doing the transmit. And there's a couple that have multiple streams for multiple radios, so we may feature more than just one set. But generically, sort of what we have for some of the components. Why software-defined radio? Why do we care? Well, we start going down the path of software-defined radio and using it just to listen to the audio portions of what's around us. And we discover very quickly that there is so much RF energy and various signals present in our environment that we probably had no idea existed. Software-defined radio is opening up these new horizons, and I use the term spectrums, for us to start listening to some of these RF events and giving us access to new stuff. If we think about some of the ways, at least one of these protocols that we're going to look at for some projects, that they chose to not allow, the security measure was security through obscurity, because you needed a radio that you could tune to specific frequencies, and then you had to find a way to decode it because it was semi-proprietary. Well, you could have taken one of the actual devices and then reverse engineered it. That was a lot of work. But with software-defined radio, we can take this one device that's multi-purpose, and it can expose us to that protocol and 12 other protocols and then 15 other protocols, and everything is available to us. So we get universal access to the RF spectrum and can inspect potentially everything. And because we're building all of this stuff in software, software can change. And we don't have to limit ourselves to one piece of hardware to decode one set of signals. We have one piece of software and some software to decode thousands of different types of signals. Software-defined radio isn't limited to specific portions of bandwidth, like my AM/FM radio will only listen to certain portions of the spectrum. Many of them feature large swaths of the spectrum at the same time and have great capabilities up to 6 gigahertz and down to the hertz range as well. Effectively, with all of this flexibility, we are now exposing ourselves to previously undiscovered or uninvestigated protocols that may have some security implication. And we are finding a lot of the quote non-standard use of RF outside of Wi-Fi, Bluetooth, DECT, Zigbee, Z-Wave in IoT and others, which have largely been unevaluated because the tools didn't exist. It was security through obscurity through single-purpose radios that had to be reverse engineered or weaponized. So what's the threat? Well, it's weird referencing a slide with your own name on it first. With the proliferation of devices that can do transmit and receive for software-defined radio and inexpensively, and the path that we've gone down this road, these become cheaper. And I see that we're going to see more and more folks using these inexpensive transmit and receive capabilities for doing data exfiltration. And we're already starting to see some of this type of stuff for credit card skimmers and so forth and so on. But I can see that we're going to see these new methods make it into enterprise, effectively affecting compromise. So myself and my former intern, Faith Alderson, she now works for us full time, so she's not my intern anymore, she's my staff. We put together a project based out of this crazy idea of, hey, we go do a pen test, we go do a physical assessment, and we drop an implant, we drop a drop box, we use rubber duckies, those types of things. And we do data exfil over standard network, Wi-Fi, maybe cellular, Ethernet outbound through the customer's firewalls. And they have the ability to detect all this, and they have had we've had in the market detection tools for those standard methods for a very long time. But what if I now go out of band, out of all of those detection tools, and build a low power FM transmitter and send the data out that way? How many people's DLP solution are looking for responder hashes going out over FM radio? There are very few organizations that do this. Usually they are 3-letter government agencies of those types of varieties in certain facilities. And I joke, I don't know that they actually do, but I can imagine that they do. So what Faith and I did was we put together this scenario where we could send very small bits of data outbound over low power FM radio. And Faith went and designed her own proprietary digital mode, a method for encoding ones and zeros into the air with forward error correction, and it was quite amazing. We got reliable transmissions at about 150 baud. We could push it to 300, and you're saying, Larry, 150 baud, 300 baud? That's slow. Like, yeah, that's okay, because we're only sending responder hashes. We'll plug in a Raspberry Pi in your network, run responder, get hashes, and then just push hashes out for me to crack, and then connect to your VPN later. So small amounts of data. And it was for something that she's like, I want to go try developing this on my own. We could reuse some of these ham radio digital modes, but they didn't have a lot of error correction and so forth. And she wanted to try something new. Absolutely. Absolutely. So we would transmit with a piece of wire on a Raspberry Pi with Pi FM, with her encoding audio into her proprietary digital mode, and then we received it via one of our RTL SDRs. The big thing we wanted to do this was, if we can think of this, we're not the first people to have done so. We probably can think of various groups that would be doing this type of data exfiltration, but we just made it so everybody can do it, and hey, this is actually a problem. Okay. So we're now sending stuff out of band. Maybe you guys need to be starting to think about detecting stuff out of band and doing some analysis on those out of band, because our current detection techniques are not taking those into account. Terrifying, isn't it? Yeah, I thought so. That's why we did the project. Okay. So we'll talk about some ways in which we could have even detected our own tool because something in the environment changed. Thinking about using it in a more traditional penetration test, it was probably not be our first avenue of attack unless we are doing RF-based testing against some specific devices in use in our customer's environment or in our enterprise environment. I wouldn't typically bring a software-defined radio to go do a network pen test unless we are specifically scoped to. However, using some software-defined radio may be valuable for performing open source intelligence, information gathering that could aid in those pen tests. If we have a significantly broader scope and or additional time, because doing this discovery can be time consuming and reverse analysis of some of the signals can take some time, we may find that these organizations have proprietary, previously unknown to them RF in their environment that we could interact with and cause some kinetic action to happen or interact with those devices on the network for a network pen test that they may have never known that they had some possible exposure to. Sometimes these esoteric, semi-esoteric attacks can be damaging, but they often take lots of time to discover. So software-defined radio wouldn't be my first avenue of attack unless I had some specific goals in mind. Use the right tool for the right job. And yeah, apple doesn't fall far from the tree. I believe in having the right tool for the right job. Not all of these software-defined radios are created equal depending on what you're going to do with them. So buy them all. That's what I did, or I was real close. We'll talk about a bunch of stuff as well. There are lots of hardware options. There are lots of software options. And there are specific items that are what you may consider a software-defined radio, but are more limited in purpose. We talked about the Yardstick 1 yesterday for Z-Wave. That's a software-defined radio, but the hardware and software is limited to specific frequency ranges and specific functions in software. It's still technically a software-defined radio, but significantly limited in scope. So buy one of those too. Yeah, get them all. Maybe not. I would argue there's no right fit for any one job, and some have higher budgets than others. For example, there's no right fit for no right fit for any one job. I was doing some reading several months back and found that some folks had discovered that a USB 3 to VGA dongle could be turned into a software-defined radio transmitter. These things are like $15. So they wrote a custom set of VGA drivers for the FL2000 chipset-enabled USB 3 to VGA converters to turn the chip in the VGA end that toggles a GPIO pin to create VGA signals. They just toggled it on their own frequencies of their own choosing to create FM energy, just like they do with the Raspberry Pi. And I'm like, whoa, $15 transmitter? But wait, now I might have these in my organization, and what happens if someone compromises those and is now using those for data exfil? So now there's potentially other things that we can do with some of these exfil. And they released their tools available open source, and they implemented a bunch of crazy stuff with the VGA converter. They gave us the ability to do FM radio at very close range. They gave us the ability to spoof GPS and simulate cellular networks from a USB 3 to VGA dongle. That blows my mind. There's been an explosion of software-defined radios within the market. So some of my favorites that are well within reason and within budget, one of them is the HackRF1 with two readily available, two varieties. There's the HackRF1, which is the current production model, and there was the alpha version with the HackRF Jawbreaker. The HackRF1 is the one that you're going to find. It will do receive and transmit, runs around $300, and is half duplex, so it can only transmit or it can only receive at any one time. Runs between 1 megahertz and 6 gigahertz, and can capture 20 megahertz wide at any one time, and is software updatable. And one of the recent updates made it so that we could go down to the 1 megahertz range. It was like 5 or 4 megahertz before that. The design is open source. The drivers are open source, and there's been a couple of derivatives and add-ons based on those. One was a badge that you could wear at a conference for a Chaos Communication Congress, the radio badge with a 1. So they built a clone of the HackRF1 and put it on a badge. And then for one of the add-ons, instead of having all of the computing power over USB, they built a backpack for the HackRF1 using the expansion port. So you have the computing power and display right there. So you can send and receive, and the firmware is updatable to add additional features. Massive community support, and Mike Osman, the owner of Great Scott Gadgets, very much supports the open source community and support for this device. The other one that I think is fascinating is the Blade RF. They have two varieties available, between $420 and $650. The price difference is because of the increase in FPGA capacity. These run full duplex. You pay a little bit more for them. Do full duplex, 300 megahertz to 3.8 gigahertz with 40 megahertz worth of bandwidth, double that of the HackRF. You pay a little more for it. The designs are open source. And I know this because I broke my first one, and they said, well, here's the schematic, see if you can fix it. Nope, I'm gonna go buy a new one. Massive community support. I asked in the community to see if someone could help me troubleshoot. When Nuond built these, their intent was to be able to support OpenBTS and OpenLTE out of the box using full duplex capabilities. So they wanted to be able to create a software-defined radio that could be used for all sorts of fun stuff and to create cellular base stations, picocells. That was why they built it, because none of the software-defined radios could do that and were, in their minds, were affordable. There were ones there, but they were expensive. Some other fun stuff, the one that we've provided for you guys in class to get you introduced to some of the rabbit hole for software-defined radio is the RTL SDR, and just about everybody and their mother has one of these for sale nowadays. The price range for receive only at 2.4 megahertz wide of bandwidth, itty bitty teeny, between 24 megahertz and 1.7. Some other of the chipsets can do up to 1.9, 2.0, like the Newelec E4000 one we discussed yesterday. Okay. Cheap. I've seen them as low as $8. Typically they run 20 to 35. You guys have the one from the rtlsdr.com blog, which has a temperature-controlled oscillator, which they tend not to drift as much because they are cheap devices. So the signal drift is much better. They come with a nice aluminum case that acts as a heat sink to keep the heat down. They have industry standard removable antennas, and antenna suite with the dipole antennas as well. I've only been able to find that they're closed-sourced hardware. I've even tried to buy some of the tuner chips so that I could build my own, because I want to basically build a backpack for or a shield for the Raspberry Pi that has this instead of over USB. But I didn't spend a lot of time at it, but I failed for designs and actually places where I could buy the chips. So some folks have been building their own with custom designs, such as the RTLSDR.com blog folks, and all sorts of other add-ons as well. It does require some, quote, custom drivers for Windows, Linux, and Mac OS, but they are readily available. The intent for these devices were originally digital TVB broadcasts, so you could receive digital TV in Europe, but they found that they were effectively a software-defined radio and could be repurposed as such. Some other ones that are quite fun, pretty much anything from Edis is amazing. They have several different series of software-defined radios depending on capability. They do have some that run about $5,000 that can capture the entirety of the 2.4 gigahertz spectrum, so you could sniff Bluetooth Classic all the time. The data that comes out of those is massive. It's like 800 meg per second for data for being able to analyze that. In my opinion, Edis has been the leaders in the industry. They were the folks that were really doing this for the military before software-defined radio was even available for consumers. So they've been at this a long time, and they build amazing stuff. And you pay for amazing stuff. Agreed. Okay. Another one, the AirSpy, is receive only, about $150. And then there's some new versions of the AirSpy as well. It's similar to the RTL-SDR with a couple of additional features. The biggest one is that it is intended to perform faster scanning across a frequency range. The RTL-SDR will do it. It's relatively slow. The AirSpy will do it significantly faster. And then some of the new contender to the market, the Lime SDR, the Lime SDR Mini, and so forth. But for $300, it allegedly has better receive bandwidth, full duplex, multiple radios, full duplex at the same time, which is better specs than the Edis B210 for significantly cheaper money. The one that is kind of weird for me with the Lime SDR series is that they have like their own software-defined radio store, software store. So like Google Play for our mobile devices or the Apple Store, they have like a store where you can download apps for it that way, which I think is it's kind of weird because it's their own proprietary store. But that said, they're all based on standards and can be used with many of the other projects and tools because they're all based on some standard interfaces. So good stuff there. There's a couple of other options as well, but I think these are some of the more prevalent models and ones that I've encountered and have enjoyed. So it's a roll-up of some of the feature sets for the ones that we've discussed. So you don't have to go through all the slides. You can get some ideas as to what you may want to consider price-wise and feature set-wise. Some other times, we talked about some unintentional transmitters for maybe use as a software-defined radio. We talked about the FL2000 chipset with Osmo FL2K. We can potentially do this with other options as well by toggling an input-output pin at a specific speed to send our electrical energy down a wire or a short pin, which effectively creates electromagnetic energy, which is essentially RF. And if we toggle those at a specific speed, cadence, and interval, we can, with a state change of 1 and 0 on those input-output lines, we can create RF energy and a transmitter. There's a bunch of different devices that can, in fact, do some of this type of stuff. These might be interesting to now have in our environment and for us to start doing detection of. The first one is the FL2000. We sort of mentioned that with that USB 3 to VGA converter, GPS, FM, cellular, and others. Another gentleman found that he could use a USB to TTL serial converter. So instead of sending serial data, he was toggling the serial port to generate AM and Morse code by using a serial dongle, and released some software for those as well. The Raspberry Pi also toggling one of the Broadcom processor GPIO pins with a specific cadence can, on just about all of their models that I've encountered, using either RPi-FM or RPi-TX, can create FM with RDS, POCSAG, SlowScan TV. We can do spectrum painting with waterfall displays, all sorts of neat stuff, and cheap. These things are low power and don't have a filter around their output, so they're very bad stewards of the RF spectrum. So we create a signal and we also have additional harmonics, those repeating of those signals without a filter. So they're really loud and messy. They work, but it's not very nice to the RF spectrum. We need to make sure that we have an appropriate antenna length. If we don't have an appropriate antenna length and we send RF energy into the antenna, we can cause some problems for ourselves, especially during transmit. Okay? Transmit is very important. Receive is less important, that we have the antenna length proper. But with the improper antenna length for the wavelength that we're looking, or the frequency range we're looking to receive, it will be more efficient on receive if we have the antenna at the right length, and most efficiently. On transmit, it is extremely important. So a too long antenna is inefficient, and a too short one can end in voltage standing wave ratio problems. Effectively, what this means is we're sending energy down the wire of the antenna, and if it's too short, it hits the end of the antenna and folds back. And if it's still too short, it sends that energy back into the transmitting radio that shouldn't be receiving any energy at all. And then we do that enough and we let the magic smoke out. Okay. So it's important when we transmit to have an appropriately tuned antenna for the length, for the frequency range in which we're intending to transmit. And we have some calculators here for both imperial and metric calculations. So if we want to, say, look at some various frequencies or transmit on various frequencies, we can do the math to figure out how long effectively our antenna should be to be most efficient and to prevent damage to our software-defined radio. So in my opinion, the best way for us to start finding signals with software-defined radio is to visualize what I can't see. It's, RF is invisible. So let's make it visible so I can start figuring out where some of those signals are that I may be interested in deciphering. Okay? We have a bunch of different options here, depending on the type of capabilities in which we want to dig in and with which resolution. Okay? So general visualization of the spectrum through various ranges. We have retrogram, RTL-SDR, GNU radio phosphor, GQRX, and some other stuff with RTL power and heat map over time. All right, I thought retrogram RTL-SDR was pretty neat because we can run this on some low power computing devices like a Raspberry Pi with RTL-SDR on it. And we can start to visualize the spectrum with a text-based curses display, which is decidedly low fidelity. Okay. Excellent for quick work to make sure that I'm in the right spot, and on devices that don't have a lot of processing. And I can run it over SSH. So I can put one of these things remotely and see the display of what it looks like over SSH. It's really feature deficient, It will display what's on in the spectrum. It won't give us any demodulation. It won't give us the ability to add plugins or any audio output, and we can only control it with the keyboard. But we can specify a sample rate, center frequency, and a step for some jumps that we use with the keyboard once it's started. An example of our retrogram RTL SDR. Do this over SSH, and it starts doing a fast Fourier transform sort of real-time graph for where some signals may be present, indicated by spikes depending on how strong the signal is, and will tell us where we are currently tuned in the top left. We can change this scale left or right using some of our arrow keys. Okay. Pretty simple. Okay. Hey, we have a signal at 145.5 megahertz because there's clearly a fairly large spike there. What it is, don't know, but there's something there. Maybe we should dig in with other tools. One of the ones that I really like is GNU Radio Phosphor. On the converse, compared to retrogram RTL SDR being low fidelity, GR Phosphor is very high fidelity. In that OpenCL is used for generating high-resolution displays for waterfall displays, fast Fourier transforms, and so forth. Great for digging into more detailed signals with significantly more granularity for things that we might not see with some of our other tools. Much like retrogram RTL SDR, no demodulation, no audio output, and no plugins. And we can operate it standalone right with our software-defined radio, or we can implement it within other GNU Radio projects as a GNU Radio block. So a little bit more high fidelity than the last one. We can do manual frequency selection with a slider. We can see some fast Fourier transform graphs, and we can set peaks when things have been at a higher peak. In real time for a fast Fourier transform, and a historical waterfall when signals have been present or not present, changing over time based on strength. A little bit different than retrogram. I like this one. With some of the other tools, you don't get nearly the same resolution with your historical waterfall. So sometimes with GR Phosphor, it's a heck of a lot easier to pick out some of these signals you might otherwise miss, especially those that don't have a lot of amplitude or are very quiet. A general purpose one that I find myself using a lot is GQRX under Linux and the Mac. Multi-platform gives us the ability to use it on Windows with Pothos. I wouldn't recommend it. I go to the Mac or Linux instead. Gives us real-time fast Fourier transform display, historic waterfall display. Has the ability for us to do audio output, decoding, saving to disk, redirecting to a network port so that we can listen and grab that data on other devices. The plugin support with community-driven add-ons, and generally fairly easy to use. I'll tell you the hardest part about using GQRX is figuring out how to change the frequency. And it took me about 3 days to figure out how to change the frequency, which is kind of sad, actually. So looking at GQRX, it will either have a power button or a play button up in the top left-hand corner so that we can start activating the radio. We have our frequency selection, real-time fast Fourier transform graph, historical waterfall over time where signals are present, and our options and plugins for demodulation and all sorts of other stuff, audio output on the right. How do you change channels? Well, if I wanted to go to 105.8, I click on the 4, and I click on the top of the 4 to go up. If I wanted to go to 103, I click on the bottom of the 4 to make it go down. Yeah. It took me 3 days to figure that out. For whatever reason, that wasn't intuitive to me. I was just clicking on stuff and it would change and I'd end up going all the way around. And yeah, you click on the top to make the number go up. You click on the bottom to make the number go down. I shouldn't admit that it took me 3 days to figure that out. All right, and you guys will be using some GQRX as well. The other one, this would be some of the types of tools that I would use to detect something like vapor trail for that custom exfil tool. RTL Power and Heat Map, and they have RX tools to be able to do this with some of the other software-defined radios as well. But RTL Power coming with the RTL SDR tools with command line operation scans through a defined frequency range that you define with specific hops or intervals, and then records the level of RF energy present. So instead of just looking at 2.4 megahertz wide, we can now use this to scan hundreds of megahertz wide. But this becomes the challenge of, oh, if I'm here, what's over here? Don't know. So we attempt to scan quite fast over that, and this is why AirSpy can do a little bit better job at this. So we get a CSV values for the signal strength of the RF energy present at the time of where we were scanning for those individual intervals, and we can convert that to an image with heat map. So over time, if we run RTL Power and map it with heat map, we can detect the presence or absence of signals or state changes in RF over time. So how do we do so? The RTL SDR tools should already be installed, but if you didn't have them, we can do so with apt-get. We then run RTL Power with our frequency range from 88 to 108 megahertz with 125K interval or hop. And we set a time interval of 5 minutes that it will take 5 minutes to scan from end to end and output the data to, in this case, fmstations.csv. Let it run as long as we want, and when we're happy with the result, Control-C. Then we can go and grab the heat map Python script from GitHub, or we can download the whole package and have a bunch of other interesting scripts as well. And then we'll post-process the FM stations CSV into PNG for us to look at a historical waterfall display for our capture. Here is an example of a capture that I did while in Seattle, Washington for that exact 88 to 108 megahertz FM radio band while in a basement apartment in an Airbnb up on one of the hills in Seattle for overnight for about a 9-hour period-ish. Okay. To decipher what these sort of look like, the darker colors indicate the lack of RF energy. The brighter color indicates stronger RF energy present. So if we take a look at this particular one, it's fairly bright, meaning strong RF presence there. And down on the lower end, significantly lighter, a distinct lack of RF energy. And we can see some variation in some of these signals in that it's brighter and spread out over time. It is likely that this is some sort of atmospheric condition for the FM radio, i.e. maybe there was a radio station that was really far away that we could hear stronger or quieter depending on whether it was raining between us and them and bouncing off of clouds and so forth. But if we had something like vapor trail here, we'd see lack of energy, and then all of a sudden it would potentially get bright for when it was active, and then if we shut the radio off, the transmitter off, it would have a darker band, as in the lack of RF energy. So we could use something like this over time with some baselines to detect the change in RF energy. Let's take a look at some of the projects that folks have built already. So we don't necessarily need to reinvent the wheel. We can use these to examine some risks in some protocols. We may find similar types of things in other protocols in our environment. And gives us some ideas about some of the things we should consider about how some of these RF protocols that we're using security through obscurity may end up coming back to bite us. And even sometimes we can use these existing tools to think different about some of the things that are available. Okay. So we might not need to spend all of this time doing all of the work. Somebody may have, done the work for us, and then maybe we reinterpret the results a little differently. So I love the rtl-sdr.com blog. It seems like every day that I go there, they have 3 or 4 stories, and at least half of them are a project that I'd love to do with my software-defined radio. One of my favorite ones is to do ADS-B monitoring. ADS-B is aircraft beacons that are mandated to be on all aircraft inbound to the US by 2020. So not all aircraft have it. They should all have them soon. The ADS-B beacons on these aircraft are unencrypted data transmitted at 1090 megahertz AM. They include the plane identifier, the tail ID, its current altitude, its heading and speed, and potentially latitude and longitude information as to that's its location. So we can now use open source tools to track aircraft. That's kind of cool. So Larry, that's great. We can use dump 1090 to capture ADS-B and then draw stuff on the map, and this will be one of the things that you do during lab, and hopefully it works out really well for us. But Larry, all this stuff is available from the internet. Yeah, how do you think it got to the internet? People using tools like this to capture from the air and then republish to the various sites for flight tracking info. Great, so what's the problem? Well, someone in the open source community took some looks at the specifications for the protocol and implemented it in software-defined radio as a decode. If we can decode it, it should be fairly trivial for us to take data and encode it, meaning we could create our own ADS-B aircraft beacons. Now, transmitting those on 1090 megahertz would be illegal for us to do so because it is a licensed band, and also would be potentially dangerous, especially at reasonable power. Because I've heard from some pilots, some pilot friends of mine, that ADS-B, when received by other aircraft, can be interpreted and can be used to manipulate autopilot. I.e., if you are on a similar trajectory or a matching trajectory as another aircraft on the same altitude, on the same approximate heading, and you receive ADS-B beacon from another aircraft, oh, hey, if we continue this course, we're on the same altitude, we're going to run into each other. So we can now modify the autopilot to descend a couple hundred feet in either direction after potentially making an automated call to the towers and letting them know that we're doing so. So that becomes terrifying. If I can decode the protocol, I can potentially encode the protocol, and then I can create fake aircraft at your altitude and heading, so your autopilot changes your altitude. And do it again, it changes your altitude. And do it again and changes your altitude as we get lower and lower to ground. That's terrifying. So my good friend, renderman Brad Haynes, actually talked about this in the failures in the ADS-B protocol at DEF CON 20 and received significant attention from the FAA, who was more than happy. He had reached out to them prior to discuss, hey, this is potentially bad. And he did work with some of his friends to create an ADS-B transmitter, which they transmitted into a dummy load, meaning it didn't actually escape, and received by an actual ADS-B receiver for an aircraft in a flight simulator. And they were able to transmit that and create a fake aircraft and change the flight path of other airplanes within the flight simulator because it acted as it was supposed to. So that's kind of terrifying. Maybe not necessarily applicable to us, but think about that next time you fly. Another one that I also find is very interesting is POXAG and Flex pager traffic. POXAG and pager traffic is all unencrypted on various frequencies to broadcast with specific destination addresses or cap codes. So each pager or beeper has a unique identifier or cap code. It receives all the messages And oh, hey, that one decoded as a cap code for me. I'm going to code that message and then beep and display the message on the screen. So it receives all of the data, all of the RF energy, decodes it, and then displays the messages intended for it. It's a broadcast medium. There are still lots of folks using pagers. I've seen them used for IT systems monitoring, alarm systems, repair dispatch. The biggest one that is terrifying is healthcare. I got an article from a friend that there was a hospital in Victoria, British Columbia that was notified that their paging system, that they were using POXAG and Flex pagers, and they were transmitting electronic patient health information into the air for years. And this is this case with many, many hospitals. These people just happen to get it reported. And there's been back and forth about the release, and that the hospital was initially claiming, no, it's pager, it's secure. It's secure. It received on the ends, but in the middle, it's all unencrypted traffic that anybody can capture. It's possible that we could do transmission of these, but our transmitters for our software-defined radio are pretty low power, so it would be unlikely that we'd have lots of effect across a large distance. The question becomes, what can we receive? The big thing here is, depending where you are on the planet, it may be illegal, and there's a big asterisk there, it may be illegal for you to decode pages not destined for your cap code, not destined for you. There's been a little bit of dispute on that. The story from Canada, it is my understanding legal to do so in Canada. In the US, it is allegedly illegal. But I'm not a lawyer, nor do I stay at a Holiday Inn Express, and I'd argue that it should be legal, because if it's not legal for me to intercept and decode the messages not destined for me, how do pagers work? It's a broadcast medium. They have to capture it and demodulate and decode the message to see the cap code to determine whether or not it's for it. Well, again, it was my understanding. Apparently my understanding is wrong. It is illegal in Canada to do so. But there's some caveats and workarounds, right? Same sort of thing with the US. It is illegal to do so, but no one has ever been prosecuted. There's no case law for anyone being prosecuted for capturing and decoding pager traffic not destined for you. My understanding is that the only time anyone has been prosecuted was when there was a gentleman who was capturing pager traffic in New York City on and around 9/11, and he took the decoded data and shared it with WikiLeaks. That was the only my understanding is that was the only time anyone was prosecuted. If he had decoded those and didn't say anything to anyone, no one would have ever known. But because he shared it with a third party, they tracked him down and he was prosecuted. So be careful about some of this type of stuff. You are going to capture pager traffic in lab, and I'm going to tell you right now, the pages are intended for you. I will tell you where to listen, and all of them, regardless of cap code, are intended for your receipt, and you are permitted to decode them. Okay? So I'm going to give you permission to do so, because they're intended for you, regardless of cap code, because you are all the cap codes on this frequency. So we can use RTL-FM, some standard command line tools, to do reception of FM with specific sample rates and on specific frequencies, and then pipe the raw audio that is received from the RTL SDR to Multimon-NG, a multi-purpose tool for doing various protocol decodes. It can do DTMF, so touch tones. It can do Morse code and a bunch of other stuff as well. It can also decode POXAG and Flex pager traffic of all speeds and varieties, and does so pretty well. And you start doing this on live data, and you get some very scary stuff, very similar to those from that hospital in Victoria, British Columbia. Some other things, if you decode them, you will also see interesting information. I know of a gentleman that did some phishing work for an organization And they thought they were going to do pretty good. It was a black box test, and the organization figured they only had about 30 public email addresses, and that those folks had been pretty well educated about phishing because those internet addresses, those email addresses were searchable via Google, and they knew about it because they had searched for it. But there was a member of this particular organization that was doing the phishing campaign that had been capturing pager data for years and writing it to text files, and was also in the same local region as where this phishing campaign was being conducted for the organization. So they searched through all the log files and found 400 or 500 email addresses that had been used as part of this pager network for this organization that was being phished. So they used all of those email addresses that they discovered black box style to send those phishing messages to, and they had a great degree of success. So didn't share with a third party, just used it for open source intelligence information gathering. So questionable there as to the legality of something like that. So again, be careful. Some other type of stuff, we're rumored to have law enforcement with Stingray devices standing up of a mobile cellular tower for capturing potentially conversations and IMEI information for doing location tracking, or even just outside of the Stingray type of stuff for law enforcement, thinking about coming to DEF CON. People think they're funny and they stand up their own microcells to have your phones connect to their microcells so they can be man in the middle of your traffic. Wouldn't it be nice if we could tell when these environments change? Sure, we can do that with software-defined radio, but this becomes a little bit obtuse with some of these RTL-FM type of stuff. But if we think about how cellular towers are, they just don't pop up overnight. Well, sometimes they do, but it takes a long time. They just don't appear and disappear at random. They just don't walk away. They're usually bolted to the ground. Okay, and then one time I lost the cat. My mom almost said it just didn't get up and walk away. Wait, what? No, I did. Oh, it's a cat. So let's set a baseline, monitor over long term, and then notify when the environment changes, similar to rogue AP detection with Wi-Fi. How could we do something like this? Well, let's use tools that are intended to do something else to build our own do-it-yourself cellular tower detector, Stingray detector. Okay. The calibrate tool will use a script around the calibrate tool for cellular base station detection. The real intent for calibrate was to be able to effectively use our RTL SDRs better because they're cheap devices and they drift a little bit. The intent with calibrate is to tune our RTL SDR to a frequency that has a known use at a center frequency, i.e. cellular base stations have specific channels, specific center frequencies, and they are very strict about where they are so that they operate properly. Tune your SDR to that frequency and vary it a little bit and see where it's stronger, and then you can determine frequency drift. And it will tell you which cellular towers were found, what channel they're on, and give you the ability to then adjust some of your other stuff with your RTL SDR based on that frequency drift. So your reception of signals is more accurate. But every time you do run calibrate, it tells you what cellular towers are present and which channels they are in the area. So let's run this, create a script to inspect the values, which cellular towers are here at a fixed location. We run it at home, and cellular towers show up. In the current scan, we've got 231 and 242, and great. Current state, baseline, 231 and 232. You wait, it keeps scanning at some interval, and then all of a sudden one of them goes away. In this case, channel 242 is no longer present. We don't hear any RF energy from one of the cellular towers on channel 242 anymore. What happened? Cellular tower went away. Our baseline has changed. Then all of a sudden a new one shows up on channel 245. Wait a minute. something new showed up that in our environment, and cellular towers just don't pop up overnight, and they don't unbolt themselves from the ground and walk away. The environment has changed for cellular. Using a tool that was intended to us more effectively use our software-defined radio by figuring out where our frequency had drifted to find other stuff in our environment. So taking a pre-canned project and doing something different with it for some detection mechanisms. Some other attacks that we should consider. Capture and replay. Unauthenticated signals in our environment that may have some kinetic effect or issues with the protocols themselves. So if we had a software-defined radio that can do receive and transmit, we can capture a signal and then replay it unmodified later and see what happens. Maybe we can trim it up with audio processing tools so we're just doing the signal as opposed to these long captures. Now, capture and replay with unmodified signals works really well against unauthenticated signals, such as those that don't use rolling codes, don't perform any mutual authentication or per packet authentication, or have one-way transmitters that can't perform mutual authentication. Like this one's a bad example because it does, but some of these like presentation remotes are transmit only, and the little dongle that goes into the laptop is receive only. How can the receiver prove that the signal it got was from this device? Well, it can't transmit back to do any challenge response mechanism, so it just happily takes input. So let's capture the signal of moving the slides ahead, and then just replay it over and over again, and Larry gets really annoyed because his slides can't just keep going. Now, replay can't really be that bad, can it? Yeah, it can. In 2016, Caleb Madrigal used his HackerF to record the signals from his Jeep Patriot key fob and recorded locking and unlock events for the key fob. He captured them, split them out, and then replayed them into the air unmodified and was able to unlock and relock his Jeep without the use of the key fob, just using replay of the signals he had captured. Now, he couldn't start the car and drive away because he needed a key to do that, but how many of you, when you maybe park your car somewhere in public and you have your work laptop with you, so you go to the trunk and you put your laptop in the trunk because the trunk is a little bit more secure? What if someone had captured a couple of days ago you unlocking your car, and then while you're in the car park at the mall with your laptop in the trunk, they unlock it and then press the button to open the trunk and steal your laptop, close everything back up and lock the doors, and you don't notice until much later that the laptop is missing from the trunk? That's pretty scary. Some other ones too is the protocol in use by the Jeep Patriot in this case has been deployed to millions of vehicles. How do you fix something for both the key fob and the car itself that you have to maybe do a firmware update or change the way the radio fundamentally works for millions of devices? Trying to fix a problem like this is nigh impossible. And now you're stuck with it and it's vulnerable. So think about some of those types of attacks. Some other stuff that I find is pretty interesting is a tool called RTL433. It's a generic RTL433 industrial, scientific, and medical, or ISM band, unlicensed portions of the spectrum for use for consumer devices like Wi-Fi and presentation remotes and so forth. RTL433 is a 433 megahertz receiver for the RTL SDR. It listens to 433 megahertz, captures signals, and then decodes and analyzes the data that it receives and compares them to a list of fingerprints for known devices, 100 or more that folks have analyzed and contributed to the project. There's a bunch there that are unreliable, so not all of them are enabled by default, and we can use RTL433 either in live capture or write to disk and then subsequent decode later. We can record and play back an entire session. We can have it split out into individual chunks when data has been received, and then we can play those back later and do additional decodes. So lots of capability in the way we'd use a tool for that. When they're recorded to disk, they're recorded in standard formats so that maybe we could even capture them with RTL-433, decode them and figure out what they do, and replay them later. Maybe they're subject to replay-based attacks. This is me running RTL-433, enabling all of the protocols with the capital G in my living room. And it picked up a couple of devices. It picked up this DSC contact with a status of C3. It picked up a PCR 800, which is Oregon Scientific Weather Station devices that has, it's a rain gauge. It picked up the TGR 810, which is a temperature sensor for weather station. 17 degrees C, what is that in Fahrenheit? Relatively warm. 95% humidity, welcome to New England. And then another DSC contact, different ESN, but same status of C3. I knew what the Oregon Scientific weather sensors were, because that's my weather station. But I didn't know what DSC contact was. So I went and Googled it, and turns out they're door and window open-close sensors sold for alarm systems for ADT, one of the US's leading home and commercial alarm systems. And turns out it's my next door neighbor. He got burglarized last year, and the burglar actually climbed out the window of his living room because he had kicked the front door in and the dog was barking. And the burglar went out the window less than 15 feet from where I sit in my office, but my back was to the window, so I never saw it. So we had ADT alarm system installed after that. And now the question is, I've captured these contacts for his door and window open close. What happens if I capture one as an open? Record those to disk and replay those later. But replay an open window event while his alarm is on at 2 o'clock in the morning. What happens? We were doing some of this with Z-Wave, just spamming the window open. Say the alarm system says that it's open even though the window is actually checking in it's closed, but we're spamming it so much with an open condition that the alarm goes off. More importantly, on the converse, record the close condition and spam the alarm system, repeated replay of the window closed, and go over and open the window and see what happens. Maybe we can defeat ADT alarm systems by capture and replay software-defined radio using some fairly simple tools. We can also use RTL-433 to capture a bunch of other stuff, the less reliable captures. It will tell us that we found some stuff and then write them to disk for individual samples with the A and T. We can then later take those samples off of disk that are in standard formats and then replay them through RTL-433 and perform the decodes reading from those files. And sure enough, that particular one again was another DSC contact with a C3 event. We've talked about some purpose-built tools. The big one, GNU Radio and GNU Radio Companion, some tools for giving us the ability to create our own radios and use our own imagination. Okay. Lots of potential options here. We just now need to get creative and start understanding some digital signal processing to make effective radios. This is not necessarily something that is an easy task, and certainly simple radios are fairly easy to do. And there's lots of blocks for doing all sorts of fun stuff within GNU Radio because lots of smart people have contributed to the project. This becomes some really interesting stuff when we don't know what the heck we're attempting to query. We're not always going to reuse the same project. Sometimes we need to do it ourselves. We need to go from RF energy to bytes and figure out what is actually being transmitted. This is definitely not something for the faint of heart because you have no idea what you're potentially analyzing and you're having to reverse engineer everything possibly all by itself. We're going to need to do a heck of a lot more in-depth analysis. Okay? We're going to need to figure out its modulation type. We're going to need to figure out its encoding type, and there's multiple varieties of either one of these. And then we need to convert those ones and zeros, that binary data, into potentially something meaningful. Is it text? How do we know which individual parts trigger some individual events? Once we've analyzed it, can we take that analysis and that data to create our own retransmissions, our own transmissions in reverse, kind of like that ADS-B scenario? Okay. This is the part that gets complex and potentially time-consuming. But let's give you an idea as to how something like this can work. First, we need to know where the device that we're going to attack or analyze is transmitting. Might give us a good idea to determine the frequency by looking at some of the documentation. One of the ways that I do so is acquiring the device, turning it over and looking at the sticker on the back that has a Federal Communication Commission FCC identifier on it, on the label. This is an indicator to the records at the FCC where the device has been submitted for spurious emission testing so that it's safe to use in the RF environment. And you're probably saying to yourself, well, Larry, I don't live in the US. Why do I care about the FCC? Well, typically the FCC markings are on devices shipped all around the world, and typically they are the same for those frequency ranges because if they're shipped there, they should be operating in those as well. Okay. Those testing documents include the frequencies in which they operate on, and sometimes more data than we might expect. It may even tell us what types of modulation were in use, what type of encoding was in use. It might tell us about the symbol rate. It might tell us about the speed. It might even give us some protocol information. You might get lucky. You may just find the frequency. Oh, great, it's at 915 megahertz. All right, now I know where to look, and now I can start doing some other analysis by looking at other documentation as well. Okay. You can do so directly to query these at the FCC's website, or you can use fcc.io, which is a proxy to the FCC's website created by Dominic Spill. If you submit it here, Dominic knows which devices you're looking for. Okay. If you do it direct to the FCC knows what devices you're looking for, which they'd know from Dominic's site anyways. So you're sharing information with a third party, although I would argue that Dominic's site is a little bit easier to use. Do some captures, and then we need to do some analysis of that data. But not all of our captures are created equal. Okay? We do have the ability to have the data interoperable between tools of various varieties, and there's a couple of standard outputs for our raw RF signals as IQ data. Those formats can include complex signed, complex unsigned, and complex floating point with various degrees of resolution to determine the strength of those signals as captured within in the file. Okay. The complex floating point at 32-bit is arguably the one with the most resolution, as opposed to the some of the 8-bit complex signed or unsigned. We can convert all of these file formats with standard audio tools so that if one tool supports complex unsigned, but we only received complex signed, we can use audio tools to convert those because IQ data, the raw data coming from the radios, is identical to PCM audio data, uses the same methodology. So we can use AV convert or FFmpeg under Linux to do these conversions. And in this case, we're converting one file to another from unsigned 8-bit to floating point 32-bit little endian. Okay. So we can use one sample with different tools and we can convert back and forth. Now that we have some files in potentially the right format, we need to start inspecting that raw IQ data to see if we can recover encoding types and then eventually bits to bytes. One of the tools that we can use is in Spectrum for doing visual inspection of that raw IQ data. We can then zoom in and start looking at the various waveforms and looking at those waveforms and comparing them to known modulation type. We can do some marking to figure out what speed it's being transmitted at, looking for our symbols per second or our data rate, and looking at that output in various formats. So in this case, we have a display of some data in Spectrum where there was some data transmission, and we can start to see the waveform compare to what the waveform potential lengths are, the various peaks, and then we can start marking with the display to figure out in that one transmission what the data rate is or the symbols per second. This stuff gets more and more complex as the deeper we go. Another one to do this in a little bit more automated fashion is URH, or Universal Radio Hacker. We can do similar sort of waveform inspection over time. We can do automatic recovery of symbols per second and manual. We can then take that data and apply some standard demodulation to it and encoding and decoding, and then can help us take that resulting binary data and convert it back to some text. And we can actually use URH to take a sample, decode it, potentially change some bits, and retransmit that with specific types of software-defined radios, such as the HackRF and or the RFCAT dongle, such as a Yardstick 1. Taking a look at some of the components of Universal Radio Hacker, we've loaded in some IQ data. We're seeing that we have some waveforms available, and it tries to do some decode. And in this case, it looks like we applied the frequency shift keying demodulation to it, and it recovered a bunch of ones and zeros. And then sending that over to some additional decoder, turning those ones and zeros based on repeating patterns into packets, which we then could potentially modify. We can colorize those displays based on some of the data that we've analyzed based on those repeating patterns so that we can have better analysis for potentially source and destination and so forth. Hugely complex for trying to reverse engineer unknown signals. It takes lots and lots of time. Now the question becomes, when would I not want to use this? Well, there are plenty of opportunities when software-defined radio doesn't make a lot of sense. It's fun, it's time-consuming, but in many cases there are better purpose-built hardware for dealing with the protocols that we want to do. Sure, we can use software-defined radio to sniff Wi-Fi. A couple $100 to be able to do so. Some complex GNU radiographs from Bastian Blosel. Bastian Blosel also has some Zigbee stuff. We can do Z-Wave with software-defined radio. But in some cases, the tools that we've already experienced are much better at that. I would never use a software-defined radio to do a wireless Wi-Fi pen test. I use a Wi-Fi dongle that does sniffing and packet injection because there's a whole suite of tools and I'm ready to go. Sure, I can do the analysis of Wi-Fi with software-defined radio, but it wouldn't be my go-to tool. There's other dedicated tools that do a much better job of doing these with some dedicated radios. So that said, use the right tool for the right job. All right, we talked about a bunch of software-defined radios and picking which one, use the right one for the right job. Visualization of those signals is important for us to be able to figure out where we may want to do some analysis, and long-term can potentially do some detection. Okay? And many of the existing projects for software-defined radio out there can illustrate some deficiencies that are already present in the environment, and then we can consider using those as to weaponize them or provide some other information for other avenues of attack and or detection. All right, there are 2 labs for you guys to work on. There's ADSB and POCSAG Flex.